What's up everyone? In this tutorial we will create a procedural building inside Houdini. This tutorial is going to be an updated version of my previous procedural building tutorial, and it's going to cover a little bit more of a process of creation of modules, and also how to get the geometry into the Unreal Engine. And overall setup is going to be more procedural and more expandable for the future updating. So let me show off the end result. So the result is going to be a building that we can go ahead and just drag out these modules that we have created our geometry from. It's going to automatically update. And then there's also going to be, we will instantiate some door modules like that. And once we're done with the geometry inside Houdini, we're going to create a point cloud. And this geometry is going to be sent to the Unreal Engine. So for demonstration's sake, I went ahead and imported some of the geometry inside Unreal Engine. And so basically we are instantiating geometry that is already in the content browser. So all of the geometry, so basically we just importing the point cloud inside Unreal Engine and getting all the geometry from static meshes in the content browser. So that's what we're going to cover in this tutorial. But for the main building, we're going to cover topics like convex and concave corners, how can we instantiate them, and in the end we will have a little bit of additional controls where we can control how we instantiate our corners. Something like we would be able to change, let's say I have different corners. They're going to create this menu that we can select which corner to instantiate, and then we can basically add how many corners we want, and then we can just go ahead and add them here. So let's say I want my corners to be in different type. Just go ahead and for the convex corner, just change them to convex corners. So for this setup also we are going to have a concave corner setup, and the concave corner is going to, for me, I only have one type of concave corner, so I can't select anything else. We also have ability to select no module. You can see that if there's no module, it's not going to instantiate anything, and this is useful for the concave corners where the geometry is not really, there's no really space for the concave corner for something like this railing at the very top. Let me show how it works. So in the cases like here where it's a gap, we can basically change what's the size of this corner. So if you go ahead very close to 0, we can just close it up and that's it. In this case, when the corners there's no, so in the asset pack that I'm using, there's no really equivalent of a concave corner for the convex corners. So that's why I'm just trying to close down that concave corners. We can also change the size of the corners. So let's say my corners are this size, I can just go ahead and nudge it just enough. And the same thing for all the corners, we can change the size of these corners. So we can also, for the gables, we're going to have ability to, so for the roof, we're going to have ability to change the steepness of the roof. We can also create some offsets, so the offsets, the long and short offsets for the roof. And then we also have to specify the tiles that we are instantiating, how big they are. So this is going to be covered with these two parameters. So you can see if my tiles are, I put my tiles bigger, you can see that we have these dots, so we have these gaps. So as long as your tiles are, these parameters are set up, the geometry is going to be correctly instantiated on your roofs too. So that's for the roof options, and we can also change the basically module names that we want to instantiate across. So the setup is, because I wanted to keep my tutorial 100% instantiated geometry, I didn't want to create a new geometry. So the roof is not all that advanced. It's basically just a single roof across both of these blocks that create this building. But obviously if you wanted to create a more advanced roof, you can easily do it, because we are getting this basic roof shape, that we then instantiate our geometry over. But if you want to create your own roof more advanced and you're not really worried about instantiating geometry across it, you can make your roof as complex as you want. So for the gable options, let me go back to the geometry. So the gables, we can change the gable gable style. So in this case I have only two, and then we have some manual adjustments for them. So we can make sure that geometry fits nicely between the roof and this one, in the sides and the walls. You see there's some gaps, so this is where the roof short offset comes in handy to close it down. Then we can also go ahead and scale it, our roof, upwards to close down also any gaps. The scaling is very important because we can change our roof size, and you can see it has to scale with the geometry across. So another option for this tool is going to be check for intersections. So this is a very interesting option. If I uncheck the check for intersections, you can see that this geometry is going to be instantiated where the roof is actually intersecting. If I enable this option, you can see it's basically checked for intersection to the other geometry and said, okay, I don't want to instantiate it geometry here. So this is good in the cases when the roof is basically connected like this. But let's say my geometry is connected maybe like in this way. I could uncheck check for intersection, and this is still okay. And then I can just change the styling, and this is still okay for me. So this is another option that we're going to implement if we want to check for intersections. And then the doors. The doors are very simple. You can basically override the module that we're going to instantiate at the first floor. You can see we basically are getting the group by range node and copying these options, where we can just drag around and say where I want to get my doors. If you want to support my work, you can download this complete work file with all the custom HDAs I'm showing in this tutorial. And if you do support it, I want to get your feedback and any bug reports, and how can I improve these HDAs. So if you you can join my Discord server, or you can just write me an email with any issues you are having or any suggestions for the tool. I will keep updating these HDAs, and anyone who downloads them will get all the future updates for them for free. So that being said, let's begin tutorial. Before we go ahead and start working on our procedural building, I wanted to show the layout of the project and a couple of things that I have set up beforehand to make finding of files on disk a little bit easier. So first of all, let me show the layout of my project. So I just have a mention root directory, and I have Houdini and Unreal project folder. So in Unreal I have my Unreal project, which is opened right now, and in my Houdini folder I have just one heap file, and that's it. So this is for the project structure. It's very simple, and any geometry that's going to be generated is going to be on this root folder of the apocalyptic mansion. So for the ways that we can get our find our files a little bit easier, you can go ahead and go to your Houdini folder under the packages directory. Go ahead and set up your JSON file with the new environment variable that points to this root directory. So what I have here, I have a environment variable mention, and that means that I can reference basically this environment variable inside Houdini and also in Unreal Engine, and to get this folder path. Since I have all my geometry there, I won't have to write all this along the line every time. So this is definitely something that you should use to make your workflow a lot easier. And of course I have also installed Houdini engine, and that's pretty much it for the setup of the project. Now that we have learned a little bit about the layout of the project, let's start working on our procedural building. So first of all, I want to pay your attention to these building modules. Let's take a look at some of them, one of them at least. You can see that they are aligned along the x-axis. So in the node that we're going to use, which is the buildings from patterns inside Houdini labs node. The HDI actually requires that this geometry is actually aligned along the y-axis on the Unreal side, and since the y and z-axis is flipped in the Houdini, that means inside the Houdini it should be aligned along the positive y-axis. The first big challenge is to basically rotate all of these modular pieces to be aligned correctly. So this can be pretty challenging because there's a lot of these, and there's really there has to be a better way for us to do it than doing it manually. And there is, because we have Houdini, so we could do it through Unreal Engine. We can basically, there's like an option to do it through the modeling, or you could make like a blueprint also do it from Unreal. But since this is a Houdini tutorial, I want to show how we can basically export the geometry, do any edits we want to do inside Houdini, and re-import this geometry, and basically override all of these files inside this folder as a new geometry, but with edits applied. So first of all, I want to go ahead and get all the geometry on the disk. So what we can do is go to the Houdini engine, and I'm going to open up my Houdini session sync. So this is going to be actually very easy with a couple of HDAs that if you going to support my tutorial, you will get, and you can try them out. And basically this HDA is going to make it very simple for you to export any geometry that you want from the Unreal Engine, or also from Unreal Engine and modify it and all of that. So let me go ahead and do this right now. So what I'm going to do is I'm just going to go ahead and in this general mesh we have 270 items. Just go ahead and select them all, and there should be, if you have installed your plugin correctly, there is an option to send to Houdini. Just press it and go ahead and open up Houdini. You can see we are now exporting all of the geometry inside the Unreal Engine on Houdini, and all of these files are going to be located under the Unreal content. So you can see, and there's no really option for me to see how many, but since we exported 270 static meshes, this should be 270 overall nodes inside, and you can take a look at them, some of them. And it's basically the points and vertices are not very interesting, but there is a lot of information that came from Unreal with these with primitive attributes. And one item that we are particularly interested in to the Unreal input mesh name. And this Unreal input mesh name attribute points to the basically a file directory inside Unreal where this mesh is located. So you can see that, take a look at this path. So inside the inside here you see it's a game, so it should be also, you see it's also a game. So if you press on it, it converts content to the game name. So that can be a little bit confusing, but basically when you see this content, this is a game folder name inside the attribute. So what I'm going to do is go ahead and export all of these inside, all of the geometries on the disk as a BGOs. So what I'm going to do is go ahead, and you can see it's even exported like an environment sphere or something. So that's fine though. What I'm going to do is showcase my first custom node that I created, which is the save Unreal geometry. So all the custom nodes that I showed are actually documented. So I try to add some particularities for these nodes so that you can read up on them, and they should be, if you support my work, you can go ahead and read up about a little bit more about them, and all of them are going to be opened. I'm going to even try to, if you want to learn a little bit more about how the node is set up, I'm probably going to add a little bit more annotation for them. So it's definitely want you encourage to go inside these nodes and learn about them, because there's because these workflows are really well, it's really beneficial for you to also know how they work internally, because we're using these top networks, which is basically a way for us to automate work inside Houdini. and marshal our geometry. So this node only requires us to input this subnetwork that comes from the Unreal Engine. So basically just connect it inside here. And the parameters are pretty simple. So let me go through them. So first of all, I want to give these, since we have to save these files, we want to get a unique name for each one of these files. And this is where the Unreal input mesh name comes into handy. What we want to do is basically just parse information from this string and get the last part of this, basically get the name of the item from the content browser meshes general. So basically we want to extract this name from this attribute as our file name that we're going to save on disk. So this is where the regular expressions come in handy. And if you are not familiar with regular expressions, this is basically more advanced wildcards from Houdini. So you know that in group you can use like an asterisk to identify deletion of all the groups, or like it's not a caret to exclude some of the groups. And this is basically more advanced version of the regular expression. It's more advanced version of the wildcard. And to actually showcase how it works, I have set up my one of the. So if you want to go ahead and test out your regular expressions, you can go to the regex 101. I'm going to paste this very simple regular expression that is provided for you at the beginning by default, and I pasted one of these attribute values inside the string that you want to test against. So you can see I pasted the path of the static mesh, one of the static basically attribute values, and the regular expression that is provided by default. You can see that it basically has split string into two parts: everything before the last dot and everything after it. And you can see that it has given the and with this syntax of $p, we can give it a group, which Houdini then can use as a value when we export our data. So that means we have two groups, path group, and also have a name group. And since we are matching against this value inside here, we can use this extracted name attribute part after the last dot to use it as a file name inside here. And to showcase how it works, we can go ahead and generate static work items. And if you take a look at, press on one of these dots, which basically identifies one exported file. And if you press on this file name here, you can see it's static mesh cage 1. You can see it basically changes dynamically with the name that is going to be exported. So this is already super beneficial for us to make sure that we have a unique names for all of our files. But I do not want to stop here, because I also want to give it a unique subdirectories for all of these files. So right now, if we would export it, all of the files will be basically just thrown into one directory. So that's not super beneficial for us. So what I'm going to do is use my second regular expression, and the regular expression second one is a little bit more advanced. Let me showcase it inside here. So the second regular expression is the beginning is the same, but now we are separating our static mesh name into three parts: everything before the first underscore and everything after the last underscore. And you can see this pink one is basically which I name a common name. So that means we can use this common name group that has been extracted as our subdirectory from our for our files that all have this basement name in the middle. So this is going to be super beneficial for us. And if you go ahead and use this one in the as a here, so I use the P at front of it because this is a PDG attribute, common name. So this is already so to see the updates, you have to go ahead and dirty it and generate it again. And if you take a look at, press on some of these work items and press on subdirectory, you can see we are now getting our subdirectory door front, and some of these going to be the same subdirectories. Some of these files are going to be thrown into a single directory. And if you want to visualize how many directories you're going to use, we can inside basically we can visualize it with the work items instead of each file, instead of these work items being represented by each dot, we can represent the directories with these dots, and this is where the visualize part comes into handy. You can go ahead and just copy the name of the attribute to visualize the common name attribute, how it's going to be partitioned. If you go ahead and cancel the dirty all and generate static work items, right now we're going to have only 102 directories, and if you press on them, let's find some of these. There's going to be multiple outputs. You can see here we go. Expected output is actually 10 files, and you can see that the roof edge common name we have actually 10. You can see that for the roof edge there are actually 10 different geometries going to be into the single directory. So this is where the this is very beneficial for us. So it is, in this case, this works because the naming scheme is uniform for all the static meshes. So, and if you have different naming scheme, that obviously means that you have to go ahead and test out your regular expression and paste it inside here. And I would really suggest you, if you want to do this, go ahead and just paste your static mesh name here and then just create a regular expression that matches data that you want to extract from. So in this case, this is going to work just fine. And then my output directory is going to be, and this is where my mention environment variable going to come in handy. Let's call this geo, and let's call this Unreal Geo. So this is going to create a new directory. So if you go ahead and dirty all, and let's try to, so there is two options for us to cook in the PDG. We can go, we do cook type out of process. That means for each one of these files that we export, it's going to create a new instance of Houdini and save it. But since the operation that we are doing is really light, most of the time this is not really worth it for us to do it out of process. We can do it in process. That means that basically one work item at a time, but since we have already opened up our Houdini instance, it's going to be super fast when saving it. But I did run into I would presume that something that that's a bug, and let me try to bake it out and see if this bug happens. So let's go ahead and cook output node. Okay, it actually works. So you can see we're now cooking out. You can see we have our new geometry, Unreal Geo, and this is where all the files are being saved to. So I want to talk a little bit about this bug that I found. So it was really weird because when I have my cook type to the you can see we have already completed. We have exported all the geometry on the disk, and you can see we have really nice directories with the file types So I would definitely recommend you to start with the in-process cook type, but by default I have put it on the auto process because I found I would presume that that's a bug because it would basically not cook. It would immediately show that it has completed cooking and all of the files, and there would be no output of these work items. So I definitely would recommend you, if you're getting this tool, try to in-process before to make sure, because it's going to be a lot faster. Like if I would have cooked it out on auto process, it probably take like a minute because of the creation of new Unreal instances for each one of the files. So that's since we're doing it really, this is a really simple process. We're doing it. It's not really worth it. So we have basically exported all of our files, and we can go ahead and close this Unreal. You can go ahead and inside Houdini engine, close Houdini session sync. So it's going to go ahead and close the Unreal instance that I have just opened up. And now I want to go ahead and rotate my geometry. And to demonstrate how it works, I want to go ahead and take something like a wall file to demonstrate how it works on the single file. Actually, let's do it on the 3 files. I'm going to copy them, I'm going to put them inside the new folder, test geo, to showcase some other tool that I have created, because I don't want to touch geometry, because this geometry is going to be all going to be modified in the batches. I do not want to touch it right now. I want to showcase the tool on the test geometry and then do it in the batches when I have showed how it works. So let's go ahead and open my Houdini file. So inside here I want to go ahead and showcase how can we easily rotate our file. So it will be, as you might imagine, we just basically get the file, rotate it, and save it, and basically overwrite the exported, basically overwrite the file. So this is actually not all that simple without the top network or without some, well, actually it will be pretty, well, it will basically doing the same thing a lot of the times because of the, basically we are doing the same thing all the time. So let me go ahead and, by default you would go file, let's go to the heap file mention. So mention, so geo, test geo, let's load any one of these. So we have our geometry, we want to rotate it around the 90 degrees. So we have to do it in the, so for us, so we have to basically make sure that the wall faces positive z-axis, positive x-axis, and it is allowing the along the z-axis. So put down the transform. So this will be positive 90 degrees. So it's going to be positive 90 degrees. So we have to rotate it like that. So, and to do it more sustainably, I want to showcase my next node, which is a file, actually geometry nudger. So geometry nudger is very nice because we can apply operations that we want to do on all of the geometry and then basically overwrite these files. So let me go ahead and point to my test geometry. And this also node uses the top network. So generate, point to the geometry root directory. So the idea is that there's a root directory, and if there are subdirectories inside this root directory, there's going to be generated a menu where you can select the subdirectory. And since I do not have it, there's not going to be anything here. So, and if this is left empty, it's basically just ignored. And then the pattern to get the files, and by default all of these are going to be BGO files, and the asterisk means that get all the BGO files. And if you press on generate static work items, they should get my 3 geometry files. If you're going to go ahead and just flip between them, you can see we have these files. But we want to do is basically go ahead and there's a modify geometry, or basically the common thing that you want to probably do is translate geometry. So just go ahead and press 90 degrees, and that's it. And it has applied this operation on all of this geometry. And what's cool about this file, that it has actually option for you to apply custom edits. If you go ahead and double click on it, it's going to give us so you might have noticed that some of the nodes inside Houdini has like something called a dive target. So that means the node still is being locked, but you can go ahead and enter it, and you can basically go ahead and modify your network here. And let's say I wanted to add like an attribute. I put down the wrangle node, add test equals this is test. Let's go to the string attribute. So I just put down a string, create a new attribute on the, let's actually go ahead and do it on the detail attribute. For the geometry, you can see I have a string attribute. Now let's go back to the node, and we can go ahead and apply this attribute by using apply custom edits. So you see if I check this box, now we have written also this attribute to the geometry, and if we save it, we have basically written out this geometry also along with its rotation. We have updated this geometry. And when it comes to the saving of the file, you can use either the source. So if you put it to the source, that means that the geometry is going to be overwritten. So you have to be careful about using this, because there's no way of getting the previous files without the edits back. So if you want to use basically you want to generate a new geometry from the source, you can press on new location, and since most likely you want to save the geometry somewhere near the root directory, I have option for you to copy root directory. You're going to copy this one, and if I want to say I want to create new geometry inside like a edited geo, and I say that's fine, it's going to create these new files in this directory and not overwrite them. And all I have to do is make sure that generate select work items and just cook output node. And it's going to pop up if you want to cook all like work items. Press on cook. You can see it has now cooked out, and you can see it also has option for the cook type. So by default it's set to in process because I had no real problems with the in process for this node. So so this is going to be super fast. You can see we have already exported them, and if you start to go ahead and detail and generate like work items, so you can see the geometry here is not modified. It's basically the same because we have not overwritten it. But if you want to see the geometry that we have got here, another node that we can use a file node obviously, or another node that I have made is actually very nice for just flipping through the files on disk, which is called the file scrubber. So let me go ahead and point to the, so this goes the geo, test geo, edited geo, that's it. So the file scrubber is very nice because it has this parameter, integer parameter, where you can basically just go through it. It's going to set this file parameter. You can just see without selecting like from drop-down menu what files are on the in directory. So this is a really nice utility node for you to have. So, and you can see that if you put our rotation to 0 on our source geometry, this is not rotated at all. If you go to our file scrubber, you can see this geometry is rotated. And if you go to if you load the entire geometry, so instead of the packed primitive but all geometry, you can see we have our test also attribute written out. So this is really nice to have. So, and how we can also export this geometry back to Unreal Engine. I'm going to show it right now. So inside Unreal Engine, let's go ahead and create a new level to showcase how we can get it back inside Unreal Engine. So by default there's actually a new HDA file. So by default there's actually a default HDA file on the disk that comes with the ability to load the BGO files. So if you go to on the owl and press on the geo, and if you go ahead and use the Houdini asset filter, so you can see there's a Houdini BGO import. Just drop it down here. And what I want to do is go ahead and point our, go ahead and start your Houdini session sync, Houdini session. You want to go ahead and point to our, geometry, Unreal geometry, or test geometry inside here, edited geo. So inside here, let me go ahead and copy this file, anything after the environment variable. Let's go to in this asset, that's going to be geometry file. So now we can use our mention / edited geo. Actually I forgot, because there's actually the manual writing inside here is not going to work because of this parameter inside Houdini is set up as a string parameter, but it has set up as a directory, as a file type. That means whenever I write manually inside here, it's not going to accept a string. You have to use this one. So inside here, I want to go ahead and use this edited file geo. Select this one. You can see we have imported our geometry. Let's rotate it. Let's take a look at how it looks. So it looks weird because of some of the issues of because of the geometry has some parallax effect on it, and we have to actually modify some of the attributes that I'm going to use on the patch mode. So the idea is for us to overwrite this file inside in the content browser. Let me go ahead and see the general strings. So for now let's just presume that this geometry looks correct, and we want to overwrite our wall inside here. So geometry we imported is wall f. Let me go ahead and copy this name. Inside Unreal Engine, go to the Houdini BGO import. You can press on this refine proxy. You can see that we can specify the name of the bake name. So I want to make sure that our bake name is this name that we have in a static mesh in the content browser. Let's actually go ahead and find this file and let's drag it out. So this is the original file and this is the imported. And let's see how we can update it with this one. We're going to presume that this looks correct for now because we're going to fix it in the batch export. But for now, let's just assume this looks correct. We want to update it. So inside Houdini asset, we have pointed our bake name as the same name of the original geometry, and we want to put our bake folder as in a folder where this geometry is located. So that means it's going to be game, Albert Manor, meshes, general. So we have now pointing to the correct bake folder, and we want to make sure that we actually overwrite our geometry. So there should be an option for you to... Let's make sure that we also remove HDA output after the bake, and we want to also replace previous bake. So if we do not press this one, that means that this geometry is not going to be replaced, just an index is going to be added to it. So we want to make sure that we actually replace it. So we are pointing to the right folder. We have set up our name identical to the original one, and if you go ahead and bake it, so you can see we have now baked our geometry. And if you go ahead and take a look at it, we have now rotated the geometry along the y-axis. So this looks incorrect, but we're going to fix that. But we have basically went ahead and updated our static mesh from inside the content browser, overwritten with the one that it has been orientated. And now let's talk a little bit about why this looks incorrect. So this was kind of like so this should probably be this case by case issue, but the idea is that there's a couple of attributes that we have to also rotate on the geometry for this parallax effect to be like this. So if you're not using this effect, this actually most of the time this is going to re-import just right. But if you're not using, if you have something like these effects, you want to go ahead and apply some modification on the geometry on some of the attributes that came from Unreal Engine. And to showcase it, I'm going to do it with the batch method. So let me go ahead and go to the Houdini engine. Actually, let's go ahead and let's go to the Houdini, and let's actually go ahead and do this with the main geometry. So let me go ahead and point to the geo and Unreal Geo, and for now I want to only find my walls. So what I can do is basically put asterisk on both sides and say wall. If we go ahead and generate our static block items, it should be... Oh, right, we have to also put on the recursive, because all of our geometries inside directories. That means we have to also use the recursive to search all those directories. If you go ahead and search for all of them, you can see we have 39 walls. So this should be from floor 1, 2, and 3, all the geometries. So what I do is go ahead and we want to go ahead and instead of rotating, so we could rotate it along with using this, but since we want to also apply this rotation to the attributes that has come from the Unreal Engine, and these attributes are these tangent attributes. So there's a tangent u and tangent v attribute that we also want to rotate by 90 degrees. So we're going to do all of our edits. So we're not going to touch these default transforms. We're going to go ahead inside the div target of this node. Go ahead and match content description. Inside here I have set up, let's delete this test. I have already set up one of the strings. So this I have already set up. So let me show how it works. So in this custom edit, I am rotating it by 90 degrees. And important thing that I am actually outputting our X-form matrix as a detail attribute that says how we have rotated this geometry. And we just basically go to the attribute wrangle and run over the vertices, because this geometry is a vertex, and because these attributes are vertex attributes that we want to modify. And if you want to apply this rotation to those attributes, we have to basically use multiply it by that matrix. So it's very simple. We're just multiplying these tangent u and tangent v attributes with the x form of the transform node, and that's basically it. And if you go ahead and we can dirty all, generate static block items, it should be aligned correctly. Make sure that you apply custom edit, and let me actually also bake it out on the edit. So let me go ahead and delete this one, and let's cook output node. We're going to create all those files inside here, and let's try out to re-import it and see how it works right now. So let's go to our BGO import node, go to the geometry to import, just select the wall, and now our walls looks a lot better, and this effect seems to work just nice, just correct. So if you take a look at so this should be the original wall. Let's take a look at them. I mean, they should probably look basically. So this is an actually different wall. You see the effect is basically the same if you take a look at it. So this is how I try to fix the issue that came from the Unreal Engine. So there's probably maybe some other way to do it, and but we will basically fix the issue with the weird parallax of the shader that has been set up here. Now that I have shown how can you do it with a single geometry, we want to do it on all of these geometry. So this is where the next HDI node that I have created comes in handy. And before that, I want to show the really cool things that has been added to the Houdini engine inside Unreal is these Houdini tools options. So what you could do is drag your Houdini digital assets into the content browser, or you can import your HDAs and also have like a dedicated tab for them inside this Houdini tools tab. So what you could do is set up your HDA in something like here, in this kind of so there's a bunch of documentation, but this basically means that there's a Houdini tools, some couple of JSON files, and the HDA is actually located into dedicated folder. And if you go ahead and if it has been set up properly, which I'm going to also, if you support my work, you will get this HDA. What you can do is basically this folder, you can go ahead and take this import Houdini tools package and just point to this directory inside here. You go to paste it inside here and say import. You can see it has, since there's a bunch of JSON files that Houdini engine reads, it has shown it's imported one HDA file. If you go ahead and press OK, you can see we do not have to store our HDAs in the content browser inside Unreal Engine. We can also basically instantiate our HDAs from this really nice menu up here. So inside here, I'm going to go ahead and instantiate at origin this HDA that's going to batch import our geometry. So let's go to this geometry. And this time we are going to use, instead of doing it with a single file, we're going to use this PDG asset link. So this is basically a separate menu we're doing it all after under the separate menu, so it has a little bit of a different UI. We have to orientate along with. So first of all, I want to go ahead to the PDG, actually go to the Houdini parameters. I want to make sure that we go to the cook type, so we can use it as a single cook type, which is basically the same one that comes with the default Houdini, which I showcased at the before. Default HDA is just importing a single BGO, but since we want to do it on all of our geometry, I want to go ahead and use a PDG. So in the PDG, I want to point to our geometry that we just saved. So let's go to the edited geo. Let's go ahead and copy here. So directory is going to be mentioned, forward, geo, toast geo, edit geo. This should be correctly set up. So the subdirectory, there's no subdirectories in it, so that's fine. So the file name pattern, all of the BGOs, that's fine. I'm going to just to make sure I dirty all, and let me go ahead and just so by default we have to make sure that we actually get our we want to also make sure that our names come into the so basically our created names that go in once they are baked out are the same name of the files. So since my name files are equivalent to the static mesh names on the content browser, I have already taken care of the naming of these, and inside the HDA, in this custom HDA, there basically we can use either the file name attribute, a file name as the file name that's going to be used when the geometry is baked out in the content browser, or we can give it as custom name, and the custom name would be this string plus the item index on it. So that's not really useful for us, so I'm going to use the file name. And we can also use a prefix, something like a static mesh, if we are doing it with the custom geometry. So I'm not really sure how it's going to work out now. Let me go ahead and press to cook. So you can see we are now cooking, and if we are doing it correctly, the geometry should appear inside here. So the cooking is just a generation of geometry. It's not going to actually bake out anything. So this is all just temporary geometry that will be deleted if the so basically it's not going to be saved, it's just a temporary geometry. So it's going to maybe hitch up. I hope this video is not going to crash. So we have baked it out. Actually still baking, so let's just wait a bit. So okay, so let me just wait out. Okay, so we have basically re-imported, so this geometry has been cooked out, and now what I do is go ahead and bake it. So baking is actually baking it to the content browser. And important thing we want to so in the baking we want to make sure that we point to our meshes general, to our bake folder inside here. Just copy here, go to the bake folder. We have to modify it under the PDG under Houdini PDG asset link. So there's basically there's a basic bake for the single files bake folder, but since you're using a PDG, you want to make sure that we are actually under the Houdini PDG asset link, and just go to the bake folder and paste it our general mesh folder. And this should basically be, we should basically everything is set up correctly. And if we have done it correctly, all of the geometry should be basically re-imported and rotated, and we are overriding it. And there's actually should maybe for the, let's actually make sure that we actually go ahead and replace existing assets. That should probably be good. And just to make sure that actually, so I'm not really sure how important it is, but let's actually press on replace previous bake, so maybe under the basic bake node. So let me go ahead and trade our cook output. Actually we have to use a bake button. We're now baking it. You can see we have updated all of our geometry and it has been rotated, so all the walls have been rotated by 90 degrees. If you take a look at it, this should look just fine with all of the parallax also, with the parallax effect also. So yeah, so you can see that we have easily rotated all of our geometry and we could have created a new custom modules from the Houdini, whatever we wanted with this workflow. So in this case, I'm not really going to create a new geometry modules. I just want to go ahead and rotate them. So I'm not going to talk more about this rotation of modules anymore. So if you see the geometry that has been rotated, so you can assume that I'm using this this workflow for all the pieces to make sure that I am rotating them correctly from Houdini, from Unreal to Houdini and back. So this has already taken pretty much. There's a lot of time I have talked about this, so this is a really important thing to talk about because the geometry most likely when you get is not going to be completely ready for the building from patterns node. And to make sure that so this geometry can stay here, we can just go ahead and create a new level. We can say press don't save, and these walls should all of these walls should still be correctly oriented since we have imported them. So yeah, so that's it for the exporting. Let's go ahead and start working on our actual building. Now that we have orientated and got our geometry out of the Unreal Engine and exported it back in correct orientation, we have to tackle the next challenge, which is actually going ahead and combining some of these geometry together. It's because right now they are just the modules and there's no really, it is not a complete wall that we can go ahead and instantiate. Because this wall should probably have like something like a window. Let's drag out some windows like that. And there's also a curtains assets also. So we probably also want some curtains for these walls, something like this. And to make sure that since we're not going to, in this tutorial at least, not going to create interior, we want to make sure that once we render it, it doesn't have like a black like a void behind it, so there's actually a really nice asset of the interior box asset. And all of these has been adjusted to be aligned along the correct axis, so with the workflow I showed just before. See, there's probably a good idea is to have this box behind, so it looks a little bit better when we render it outside of it. So this is quite a big challenge for us to combine it and not to create a new geometry. So what's going to do is actually create an instance for each one of these geometry pieces, and each one of these pieces is going to be basically just a reference to these meshes on the content browser. We're not going to, so there's two ways we could probably do this. We could create a new geometry, which is basically just a combination of all of these together, and create a new module, which would be a static way of doing it. Or we could create we could orientate basically Houdini instance points, and just and these points just points to the meshes on the disk that are dynamic. We can basically switch out between the different windows and different setups very easily without hard baking out an entirely new module on it. So this is where this can actually be pretty challenging to do it. So that's why I have created another tool for you to check out, and maybe if you like it, maybe buy my stuff. So let me go ahead and let me show you it. So first of all, I have go ahead and got my modules, and this time the node is called Geometry Compositor. So Geometry Compositor is probably the most involved node that I have created for this tutorial, and this involves the combining different geometry. So first of all, I want to start with my wall. So I have my geometry. Let's go ahead and get my geometry. So come Geo, Unreal Geo, Geometry Walls, floor 1. And if you enter it, you can see we have already load it in, and you can see we can also, there's also some like just like with the file scrubber node, we have ability to scrub through different geometries here, and there's also option for you to color the currently selected geometry, which comes into handy with the viewer state. So let's say I want to maybe generate a simple wall with one window. Let's start pretty basic like that. I want to now import my window, so I'm going to press on duplicate on this one. This is going to create a new instance of this multi-parameter, and if you press on 1, and if you go into the viewer state, we can now use button D and F to switch between these geometries, and since they are the same, the coloring looks a little weird, but we go ahead and take one of these. You can see we have basically we have imported new geometry. So in this case, I want to get my window like that, and now you can see we have all my windows here, and to make sure that you can select whatever window you want, and then just drag it in the place. Just write a little bit of alignment. So this viewer state is not the best. It's kinda came as a last addition for the tool, but it is very useful. And now you can basically select between different geometries and move them around using the viewer state. Once you're inside the viewer state, you can see there's actually a little bit of a help also for the viewer state. What geometry is now handled, edited, and then you can press D and F to cycle between geometries. And now let's duplicate this again, and let's get our curtains. So the curtains, just go ahead and select the curtains. So the coloring is actually very useful for you to see the location, which geometry is actually selected. So the curtains are here. So it's kind of hard to see which curtains are these, but it doesn't really matter. They're using an alpha colors mask material to so they are look kind of same inside the Houdini. Now I want to get my interior box, so go ahead and duplicate it again and get our interior cube actually. So the cube is probably the one that we have to go ahead and scale it. I'm going to just put it pretty close to the wall, something like this. And now that I have created my modular piece, I want to go ahead and show how it would look inside Unreal Engine. So first of all, this tool works with the imported geometry, and this is a packed primitive, so we do not have any actual. So this geometry is just a reference to the other geometry on disk, and if you go to the primitive attributes, you can see that these are basically just 4 points that reference geometry on disk. So if we delete this geometry on disk, this packed primitive would basically break. So what we want to do is we don't want to, and this is good because we don't want to actually generate any geometry. We just want to create an instance. We want to transfer to the Houdini, to the Unreal Engine, an instance point. So this is why this tool is good, because it has automatically set up our attributes that are needed for the rotation and transformation of the geometry correctly inside Unreal Engine. If you go to the points, so whenever we instantiate geometry inside Houdini, we need our normal, we need our up vector, and also we need our scale. So you can see that scale is also everywhere is the same, except for the interior cube, which we have scaled up to match the window. And we basically want to extract points. So let's do this for each. So we're going to run through each primitive. We're going to extract the point. Extract all points. So this is going to leave our attributes intact. Now I want to use unpack. So since this geometry doesn't have any, right now this is just a reference, we want to get our Unreal path attributes, so we have to unpack this geometry. Now we have unpacked it, let's go to here. So I want to use Unreal input mesh name as an Unreal instance attribute on these points. So put down attribute triangle, connect 1, 0 and 1 input. So first of all I want to go ahead and get my attribute value. So string let's call this Unreal instance equals, so that's going to be prim, so this is going to be 1 for the reference, and the attribute name is Unreal input mesh name. Input mesh name. And for the primitive that we want to sample from, we can just put it 0, because for these they are all basically the same for all of these. And then this fetched attribute we want to set as our s at Unreal instance equals Unreal instance. And that's pretty much it. Let's take a look at this attribute. You can see we have written our Unreal instance on our points, and if you go to the end of the loop, you can see all we have is these points. And if you go ahead and visualize the something like an up and normal attribute, you can see they are pointing how the geometry is going to be aligned in the Unreal Engine. And all I want to do to demonstrate how it's going to work is put down a file node. I want to go ahead and save it. I'm going to use my mention test module. I'm going to overwrite my geometry. I'm going to write the file. I have written it out. Let's go to the Houdini, to the Unreal Engine. Let me go ahead and delete these modules. I'm going to use my import geometry HD. I'm going to go ahead and for the cook type right now, I'm going to use my single cook. So for the directory, I'm going to go ahead and use just going to copy it for the little bit faster workflow. Just press enter. And another feature for this HDA is that there is a file, so it's a little bit buggy inside Unreal Engine, but there are ability to create automatic menu items, drop-down menu items with the scripts, with the Python script inside Unreal, inside the Houdini, and this feature also works inside Unreal Engine, but it's a little buggy. So if it doesn't work, so you try to maybe rebuild the tool, but in this time it works just fine. And you can see that once we point to the directory, it has created this drop-down menu, and I have my test module PGO. If you go ahead and import it, you can see we have this geometry. It has been scaled correctly and also imported correctly. And if you take a look at the what it has a Houdini asset component, and we have 4 static meshes. And if you take a look at all of these static meshes are references to the geometry that has already been imported. So we have not imported any geometry, we have just imported points that instantiate this geometry. So that means that this is going to be really quick and optimized for rendering. This geometry is going to be really quick to render that here. And you can imagine using this workflow, we can create entire buildings from these building blocks by combining the geometries into subset of points to import, and then use those subsets to instantiate using the geometry, using the building from patterns node. So what I'm going to do right now is just set up a basic building modules. So you don't have to do pretty see how I'm doing it, because of it's basically going to be the same. I'm going to create a couple of modules for two floors, and I'm going to be right back. So for the most basic setup, I only have 2 modules, and actually 3, and 2 of them are actually composited from the different geometry, and the other one is actually just a roof edge single geometry piece. So I have used even for the single piece, I have used the geometry compositor. Even though if I'm not compositing geometry together, I could use something like a file node on this geometry, and instead of loading and making sure that I also load it as a packed primitive, I could use a load as a packed disk primitive option to load this single geometry. But since I'm using a geometry compositor for all of these, I'm using also the same. So this is important, because the way that we're going to work, we're going to unpack each one of these packed primitives and fetch data from basically instance, like I showed, the Unreal instance attribute value from the when we are actually unpacking this geometry. So this is why it's important that either so that our geometry all is packed, so when we are unpacking it, there is this attribute. And if you're and that the packed primitive point holds the instance attributes on it. So this is important for this workflow. Do it, but of course, if you have a way to get your points in other way, and as long as your instance attributes up, normal, and scale is correctly set up, it doesn't really matter as long as you have correct data on the single point that Unreal can read. And so in this case, this is the way I'm going to set up. And I'm going to set up, let's try to get our most basic setup right away so that we can work on more complex options later on. So just one piece of geometry for each floors. And even though I'm calling them floors, I'm, well, the roof edge not really a floor, but for the consistency and for the consistency's sake, I'll call this also a floor. So the naming scheme is going to be, we're going to try to implement the kind of like a uniform naming scheme. So for the modules, I call them floor 1, version 0, and that means that you can have different versions of this floor. And if you copy it, you can see that it's automatically actually going to create a V1 because the way that Houdini renaming works. Then you can basically set up as many modules you want from here, swap out this one and create your geometry here, like that. So for now, let's start with the most basic, with just one module for each floor. Now I want to go ahead and use our building utility, what's called utility, labs building generator utility node, and connect these points. And we want to use this as a building module. Basically, this is going to set a bunch of attributes on this geometry. So first, for the module name, since I want to always, since it's going to be easy for us to see what's the module name from the node name, what we can use is inside module name, op name, and just point to the actually op. It's actually op input for this node, and then input 0. You can see the module name is going to be fetched from the name of the node that has input 0 for this node. This is how we can easily name our module. You can see module name is also inside here, like that. And then for the dimensions, you want to just press on auto dimensions, and that's pretty much it. And you can just go ahead and copy both of these 3 times. I'm going to call this maybe building generator utility. Let's delete these and use it again. So the name by default is pretty long, and it's kind of cluttering the network editor. So these modules are set up. Now that we have our building modules, I want to create my corners. So the corners are unique in a way that we're going to handle them a little bit differently than the building modules. So that's because of the way that we're going to separate between concave and convex corners. We want to give some padding for these corners to have some padding between the edges. And that's why I'm going to use basically temporary corners that we're going to instantiate. That's going to give us a padding that is going to give us ability to instantiate different geometry there. There's going to be space between the wall corners. So you can imagine that something like, I'm going to write it out, so you can imagine that we have our walls. You can see we have this corner, and if you want to instantiate some custom corner, we need some little bit of a space between both walls to place this corner inside here. That means that we need our temporary corners. It's going to basically quote unquote fold the tool to leave the space for our real corner. So this is why we're using the temporary corners. So what I'm going to use, create a grid, and this is going to be our temporary corner. So let me go ahead and put size something like a 1 by 1. I'm going to rotate it, and for the sake of consistency, I'm going to just go ahead and align it also with the positive z-axis. Actually, let's rotate it back. Rows 2, and the plane is going to be X and Y and Z, and then we can, no matter the size of it, we can actually go ahead and actually let's just leave it like that. Since this is going to be temporary corner and it's going to be, let's make it maybe like a 0.5 on the side. And for temporary corner, we're going to basically use the same building generator tool node. Let me just copy it. So instead of the op name, let's use a custom name. Let's call this F1 TMP. That's going to be temporary. And for the C, let's indicate that this is a temporary corner. And just go ahead and copy this 2-3 times for each floor. And then just change the floor number. And the dimensions can basically stay the same. It doesn't really matter. Since these are temporary corners, they can stay like that. Let's go ahead and merge these all together. So just put it here. So you can probably make this a little bit more readable by putting some boxes around. But for now, this is fine. And let me save the file. And so these modules are going to sit in its own object node, because I do not want to clutter my actual network. We're going to create our modular building. So let's go inside the another network and use the object merge node. So the object merge, we want to go ahead and import our geometry. So just select this one, go to the modules, and on our merge node, accept it, and we have imported our modules inside here. That was pretty simple. So let's go ahead and start working on our, let's put down the building from patterns node. So first I want to go ahead and create some geometry that we're going to use as a template. So, and in the way that we're going to work, we're going to create our geometry. So for now, we're going to use a grid. I'm going to explain why we're going to use as a grid for the starting of the geometry, because that has to do something with how we are creating our roofs. Let me go ahead and use something like here. Very basic tool. Let's say this is our building. We want to obviously extrude it. Because of the way that the roofs are set up, there has to be some concessions, is that the correct word, on how we are actually starting to build our geometry. And we're going to start it by flat geometry, like that. That's going to be a start of it, and we're going to actually extrude it. And let's just connect it to the block out. So the object merge, so these are modules. Now we want to create our floor descriptions. So create a new labs building generator utility. Instead of the building modules, we want to floor description. So the module name for now, let's describe our floor 1. And then the expanded form, you can see there's a syntax. So basically that means, so we want to go ahead and start with our temporary corners. So remember, F1, TMP, corner. So the square brackets means that this module will be repeated one time. And that means you want to go ahead and do it at the start, at the end of it. And you want to fill the middle of it with these angled brackets. That means you want to go ahead for 1 version 0. You want to fill it with this one. And I think we also have to use expanded form. And the only thing that we have to do here, so the corners, I really didn't have much luck with these corners parameters, so I'm going to leave them at that. But for the module dimensions, this is important to say what's the height of it. So the first input can, from my experience, be left at the 0, but height is actually important. And I know that the floor 1 is actually 5 meters high. If you go ahead and to jump between two networks, what you can do is create your quick marks. So let me go ahead and create a quick mark in this network and go inside the modules and create a quick mark 1. I can quickly jump between them. So I know that in floor 1, and if you're using from my toolkit Also my toolkit, you can change the viewport really easily with the radial menu. Let's take a look at the jigsaw. They see that floor 1 is actually 5 meters long. The floor 2 is 4.5 meters long. And this one is somewhere around 0.6 meters long. So these values are important for us to have, because that's going to determine when the next floor is actually started to instantiate it. For the last floor, it doesn't really matter all that much, because there's no module above it. Above this roof, there's not going to be any new floors. So for this, we can approximately say, okay, it's 0.5 meters long, high. This module, this floor is going to be. But for the floors that's going to be connected to each other, we have to give it a precise height. So height is going to be 5 and 4.5. So let's go back. So for this, it will be 4.5, 5. Let's duplicate it. Let's actually go ahead and copy the naming scheme also for this building utility. Copy it. So for this, going to be 4.5. And the only thing we have to do, since the naming scheme is the same, go ahead and F2, F2, and F2. And that's pretty much it. And then for the last one, we have to give it, copy it again. So this is going to be 0.5. That's temporary F3, F3, and F3. And also the name has to be F3, and F3, F2. F2. So just make sure that you have not missed any. So 4.5, this looks good. And then you can just go ahead and connect it back to the. Basically, we have to go ahead and merge this all with the object, with the modules. Go ahead and select all of it, merge them together, and put it in the patterns. So here, in the patterns, you can say show random fill. Actually, it doesn't really like the. Oh, right, I need my. I have not input any building, so we need some geometry that holds this information. And from my experience, this should always be just a single quad geometry. So put down a grid, and just put down a 2x2 grid. Basically, something has to hold this information, these floor descriptions. And from my experience, any quad is going to work just fine. If there are more than basically a single quad, if there are more than one polygon for this input, from my experience, this doesn't work. So make sure that you have inputted a single quad into these generator utilities. So let's go ahead and go to this floor description. You can see we are now getting the default ones. And what's cool about this building from patterns node actually has a template building shapes. You can see it has a couple of shapes that has already been created. You can go ahead and copy these and start creating your custom module sizes also from here. So inside here I want to show floors. You can see I have my F1, and now I'm going to fill these modules. So I want to do it. So I want to one time instantiate my floor 1. That's going to mean that floor 1 is going to be inside square brackets. F2 is going to be also in square brackets. And F3 is going to be, and since the node always requires you at least one of these fill patterns, because it has to basically always have to something to fill because the tool doesn't know what's the size of the geometry you're going to be inputting. It has to fill it with something. So it always has to be filled with something, with some floor. And I think we can use it as a F3 inside here. You can see right now it's a little bit crazy. Let's go ahead and extrude it. You can see you can see if it's slower. Actually, I think we can use a F2 as a. So let's try this out. Only one time F3, but repeat F2. Try this one out. And let's make it bigger. As you can see that right now if we have more floors, it's going to instantiate the floor 2 all the time, and it's going to always cap with the floor 3 like that. You can see that we are already getting something resembling a building. And what's cool about this, and you can see that our temporary corners are being instantiated, and the size of it, we are basically leaving enough space for our corners to have something also. And one thing that I noticed that they didn't have these temporary corners for the 3rd floor, and that was actually because of I didn't name 3rd floor temporary corners correctly. I still had F2 on them. So now it should be correctly created, and you can see that our building is not that interesting for now, but you can see what we have done is pretty good step forward, because we have these temporary corners that we can go ahead and increase their size, and it's going to leave enough space for these geometries to have enough for our corners. And let's go ahead and duplicate this grid. Let's rotate it, and let's boolean them. Let's go ahead and boolean them together, union. This should work. Oh, I have to make sure this is surface, union them, and then poly extrude them. So will this work? Okay, so the work is just fine. I thought maybe we have to dissolve these edges, but the tool works just fine with them. Let me go ahead and make it bigger. So you can see we have our pretty basic building, but these corners are good start to let's start working on our corners. So the corners, we want to be able to change the corner size from the controls that we're going to create right here. So I'm not going to create a digital asset, I'm just going to create a new null node. And this null node is going to have all the controls that we can change. Let's call this control. Let's maybe color it something like green. And we're going to create a new spare parameters inside here. And we're going to basically able to modify our custom implementation of this building from pattern HDA node. So first I want to be able to change the corner sizes for all of these floors. So this is done by taking the import geometry, all of these floors, and let's go ahead and connect it to our let's connect it to the Wrangle node. So in this Wrangle node, I want to go ahead and fetch data from it. Let me go ahead and open this up inside external editor for quicker writing of code. So I want to go ahead and find all the modules that are named temporary corners. So we know that from our naming scheme, all of our corners that are temporary are called TMP. Somewhere in there, that is called TMP. So just go ahead and let's find these modules. It's actually very simple. We have to use just a string TMP module equals regular expression. Let's use a find. So there's also regular expressions inside of X. It's not as involved as the Python ones that we used, but it's still well, not the Python, the ones that from the top network that I showcased. So we have to basically just say what word we want to find, and we want to find TMP. And from the input, I want to just use s at module name. And I like to use this R in front of the string, so that means this is a raw string. And I think for in this case, it doesn't really matter, but if you have like a special characters, this should be more, it's a kind of a by use case scenario when you need the R, but I have as my habit, I always put r before the regular expressions. And then if, so basically if it has found something, it's going to be, if it hasn't found anything, it's going to return the empty string. So we're basically going to check for if the temporal module is not equal empty string, we want to go ahead and override this module dimensions size. We want to override this value that it has found. And for each floor, we can go ahead and say if the module starts with string, so let's say f1, and if it starts actually the s, so the string that we want to check is s at module name, and if it starts with f1, that means we want to go ahead and update our module name u at module dimensions. Dimension, so that's going to be x equals chf. We're going to create a new parameter, f1 corner size. This should basically, let's make this. So let's take a look at it. And you can see it doesn't do anything because we have to go ahead and set our run over primitives. And if we run our primitives, you can see we are now updating our module dimension size. And if you go ahead and use everything after this one, connect this to the merge node. And if you go ahead and take a look at this, and you go ahead and change the size of it, you can see our corners are being can be adjusted manually, whatever the size you want, whatever the corner we're going to instantiate over here. So this is the power that we're going to use the custom modules also for the corners and for all of the corners. And you can see that if this is a 0, the building node really doesn't like it. So it has to be at least a very small number as of size. So at least like something like a 0.01 is going to still create this building, but it cannot be 0. So what we're going to do is go ahead and repeat it for all of these, for all floors. So just copy it like here, just close them like that, and then do it again. Make it a little bit prettier, like that. If module is F2, change the F2. If the module is F3, into the F3, and you can see it has already updated red, because you have to at least set up some values in it. So you can see now we have our controls for all 3 corners. And this is important because of the way that we're going to work with our corners. And for the floor 3 is actually going to be a unique case for that floor because of the way the corners are set up there. We're going to talk a little bit later about that one, but the corners are basically set up, and we want to migrate these controls back to basically copy these controls to these null parameters. So let me do that in the not going to do it right now on the video, but let's just jump to the time that I have set up this control a little bit more. In the control node, I have set up a couple of more extra options that we're going to implement right now. So you can see the basic one is the corner size that we set up on the wrangle, and these parameters are just referencing the parameters on this node. So you can see we can change our corner sizes. So by default it's going to be 0.1, so that our tool doesn't break when it's at 0. So but basically this is how we're going to control the corner sizes. You see we have these temporary corners, we're going to get rid of them and place our own corners, but for now let's just keep them like that. And another cool thing that we can use, we can create our convex and concave offset for our corners. So for things that I noticed for this geometry, corner geometry can actually be a little bit of extruded. Corners can be a little bit extruded on the wall, and it would be nice for us to have have ability to basically offset these corners along the no, basically outwards or inwards to maybe nudge them a bit. So this is what we're going to use the convex offset and concave offset options for these corners that we're going to implement. That, and also we have to, since we are instantiating right now for our buildings our temporary corners, we want to go ahead and override these corner module names with our actual corners. So this is where the convex module and concave module for each floor comes in handy, where we will be able to select the module. And if you want to really nice way for you to be able to select the correct module, what you can do is go ahead and fetch the information from the input of this triangle. You can see from the input we have all of our modules as a string attributes. What we can do is basically fetch all of these values and create a menu, drop-down menu for all of these options, so that you can select from here what you want to instantiate around the concave and convex corners. So let's actually go ahead and implement this option. So go to the type properties, to parameter interface. So it's going to be very simple Python code that you can write. Let me expand it a bit. Let me actually open up my already complete one, so I can reference the code that we want to write. So inside these string parameters, go to the menu, use menu, and we can use the replace field single selection menu. And then go to the menu script, and now we have to go ahead and write our code. So first of all, we want to get the object that is our node. So each one of these scripts, we have a Python dictionary available that's going to give us all the basically object reference to this node. So we have a node. I'm going to call this node equals quarks. That's a dictionary object that is available for us, and the key is a node. So this is the object of the node that is available for this menu. We just want to create an empty list. Let's create a list equals empty square brackets, and if so then we want to create our geometry reference. So node.geometry. So if geometry. So this checks if this if this node holds any geometry, and we want to continue only if there is any geometry, because we're going to sample our geometry from it. And if we do not check for the geometry, the menu is actually going to error out if there's no connection to this node and there's no geometry to it. So we definitely want to always check for the presence of the geometry. And then we want to, if we have geometry, we want to check our module attribute. Let's call this a module attribute, and that's geo dot. So we know that this is we have to find a prim attribute, and the prim attribute is module name. Just close the brackets like that. So if we have found the module attribute, we want to get all the unique string attributes of that attribute. So we can do it basically for module attribute. Let's call this for module. In module attribute, we're going to module attribute, and there is a function that you can use, which is get all the string values on it. It's called strings. We're going to loop through all of them, and if the module dot starts with, and for if the module starts with F1, so basically this is a simple way that we can filter out our attributes to make sure that we only show for the F1 menu only the floor 1 values. We want to go ahead and append to this our empty list. Let's call this actually a menu, and we have to append it twice because the menu items need its value and its label. So menu.append, and we go to append our module, and we go to do it 2 times. And then we want to make sure that we always return something, and we can return empty if there's no geometry. We're going to return an empty list, but if there is, we're going to return a filled out menu list. So we're going to return menu always. Let's press enter. Let's take a look at it. So you can see we can now select our F1 modules. You can see it's going to be a little bit of a cutout because of the way the window is set up. We can actually go ahead and put this on the, I think it's a normal menu. So this is not going to give us ability to write manually value, which is actually good because all the modules are only the module name inside here are values, are valid values for it. You can see we can basically select all of the modules from our F1, all the modules that starts with F1. And all we have to do is go ahead and copy this one inside the next one. So go here, use menu, my bad, use menu, normal menu string, apply it again. See, we have this menu also, and now all we have to do is copy it again. And for the second floor, we want to go ahead and instead of starts with F1, starts with F2. Apply it, copy it again, use it again, normal menu, go here, apply it. So this should parse out only if you don't want to start with F2. And then do it again for the floor 3. F3. So this menu is dependent on the way that we actually set up our the way that we set up naming scheme for our modules. So as long as we follow our naming scheme, this menu is going to be really nice for us to fetch module names and set them with the custom implementation of it. And now that we have these controls set up, we want to actually implement them. So first of all, we want to get our points that we're going to instantiate our corners on. So this is where the segment output of this node comes into handy. So if we go ahead and put down a null node, let's take a look at it. So you see we have all these points, and sadly there is no attribute that can be used out of the box to separate all of these points between the floors. So we have to create our own attribute, and the way that we're going to do it, we're going to use it by the y value of these points. So the height is going to be used as a differentiating factor for each floor. So if you go ahead and put down attribute of angle node, inside here we can create a new string attribute as at, let's call this height, equals, what we can do is actually let's create a string value variable. First of all, we want to convert our float y value to the string, and there is no really, so there is a e to a function that's going to convert an integer to string, but by default there's no like a e to I guess it would be f to a. I don't think there's there's no really function for us to convert a float variable of the val value of float variable to the string value. So we have to use a sprintf function, which is actually, I'm not really sure how it is actually documented. Maybe it's basically well, how is it even documented? Formats a string like a printf but returns the value. So basically we have to format our string. It's going to return instead of the printing. So it's kind of not used for explicitly converting float values to the string, but we can use it to do it. So for the formatting, I just usually do this percentage and d. So this is for the formatting, and instead in the place of d we want to place our v at p.y value, and this should I think it should work just fine. Let's call this height, like that. If we go ahead and assign this value to our string value, let's take a look at it. So you can see the height is basically just fetched value from the so you can see they look the same, but this is actually a string and this is the float value. So this should be good enough for us to distinguish between different floors. And one thing that you can use is that there could be like a precision issues down the line if our y value is like an insanely long decimal value. What you can do is actually use a slicing on a string. So you can use a square brackets to say I only want to first four digits characters from this string value to be in this one. So you can see if you go ahead and press it, you can see we have only 6 characters, 4 characters for each one of these strings. 1, 0, dot, and 4 is going to basically be slicing. So it's going to make sure that at no point there are more than 4 characters for each attribute. And in this case, in all of the cases, it's going to work just fine because these values are not that different from one in each other. So the slicing is actually a good trick to use to make sure that values do not have any precision issues when you are converting them. Now that we have converted our y-axis to the string attribute, we can use it as a piece attribute to run over each floor. So I'm going to paste this network for the sake of speed and explain what we're actually doing here. So we're using a for each point loop and using a piece attribute, height attribute that we just set. And it's going to allow us to loop through each floor individually. So let's put it on a single path. Let me go through this one. So we're using an add node to convert these points to a single primitive, or at least to try to. You see it's going to create this ugly geometry, but that's fine because we are only interested into the edges of these polygons. Then we use a convert line to convert the polylines, these edges. You can see now they are actually separated from one in each other. So we want to go ahead and use a polypath node to create one single polyline to make it together, and then we can use dissolve flat edges node to get rid of any points that do not create a corner. And that's pretty much it. We have extracted our edges. Now what we want to do is go ahead and calculate our convex and concave corners. So you can see that these 4 points should be flagged as concave, and the rest of them should be flagged as the convex corners because of the tool's ability to separate from convex and concave corners that we're going to implement. So this is done pretty simply with this bit of code, and let me go through this really quickly. So the attributes are actually not lost on these operations. The normal attribute that we inputted inside here is still saved after all of these operations on these points, which is exactly what we need, because this normal attribute is important when we instantiate in geometry, and we have to follow this. Basically you can see that the normal attribute kind of follows to the next point, which is being to instantiate correctly geometry. And you can see in this attribute we have set up concave and convex corners. If you take a look at select these 4 points, you can see these 4 are flagged as concave, and this is done with this simple code. So first of all, we're getting the previous point. This previous point being basically at ptnum subtract 1 from it, and then the modules of number of points. We get the previous point, and we get our previous point's normal attribute. And to maybe visualize a little bit more about, I'm going to copy this one and explain what we're actually doing. So you can imagine that we have this normal, this, and this. So this is the convex, this is the concave and convex corner. So we are taking this normal from here, we are checking the previous normal, and if we move this normal here, you can see this we are creating always 90-degree corner. But if we take a look at our current point that we are checking, even if we rotate it, let's say clockwise, if we rotate it 90 degrees, you can see these going to be opposite sides. And this is where we basically check if this corner creates a, if these two corners are going to be on the opposite side, that means the corner is concave. If this corner, if let's say this is a convex corner, and let's say we go ahead and take and we rotate this corner also 90 degrees clockwise. Now this vector is going to point the same direction that the previous one. So this is going to be flagged as a convex corner. So this is the method that we're doing it, and we're doing it by rotating the previous, not the previous, the current normal of the point that we are checking, and then we are checking the dot product between the rotated current normal vector with the previous normal inside here. So the dot product will be something like this, basically how similar are the vectors. So if we have vectors something like this dot product would be 0, and if our vectors 2 are same, that's a 1. But if they point to the opposite direction, that's a -1. So if this is a and as long as let's say even if this vector is at also a little bit more than 90 degrees outwards, this is already going to be flagged as a negative 0.01 value. So anything below the 0, that means that this corner is already concave from our logic. So basically, if the dot product is smaller than 0, we flag it as a concave, and anything else is going to be convex. That's pretty much it for the logic of the concave and convex corners. And then we have to set our module pieces from our control node that we have here from the parameters. So this is done pretty simply. We are checking the module names. Let me turn off the single pass. So we are checking the module names, and we know that our temporary corners are with F1, F2 and F3 prefixes, TMP, and if it is, we are basically flagging the floor number. If this corner is basically a floor 1, we are setting the string value. We're basically using that value to fetch the parameter value from our control node using the floor from the module value that we have fetched. You can see that if we have found that the module name is F2, that means the floor is 2, and we have to use our channel reference is going to be our control F, and in our channel we have channel names are F1, F2 and F3. So we are referencing these either of these parameters inside this wrangle node, and then we check the corner type that we have set up inside here. And if this is a convex corner, we get our convex module parameter reference, and if it is a concave, we get our concave parameter reference, and this should basically set up our concave and convex corners correctly on these corners. And that's pretty much it with the corner logic. Now I want to implement our offset ability, also offset our points. And for our ability to offset our corners, I have implemented basically in the same wrangle additional logic. So let me show what we're doing inside here. So here we are referencing now also in addition to the convex and concave module, we are actually referencing also the concave offset and convex offset parameters from our control node. So these two parameters. You can see the setup is pretty simple. We have our floors, and we can basically just go ahead and offset them, convex and concave corners individually, offset them like that. And to show how it's implemented, it's pretty simple. So let me go back to the code. So we again are referencing parameters for the correct floor. Then we are getting the previous point. Again, we want to get our normals because we're going to get the vector along which we're going to offset our points, convex and concave points. So the previous point, we get our previous point, and then we get our previous point normal. And then we go ahead and lerp our current normal with the previous point inverted direction normal. And then we lerp it with 0.5. That means in the middle of it. So let me go ahead and quickly show how it works. So you can imagine we have our corners, and again, let's say we are checking this corner, and the normal is pointing that way, and the previous normal is pointing that way. So what we do is take this normal, check the previous normal, and you can imagine this vector is basically here, but since we are in our code, we are actually inverting it. We are actually creating something like here. And with the lerp function, we can basically create a gradient between these two normals, where we are linearly interpolating between them. And with the linear interpolation of 0.5, we're going to create a vector right at the middle of it. And that means this is going to be our vector that we are going to slide along our corners. And that's basically it. There's a couple of... So for the convex corners, our offset direction is multiplied by -1 to make sure that our logic is consistent between convex and concave corners. So you can imagine that for the convex corners, if we lerp it, it's going to be inwards, and for the concave, it's going to be outwards. So, and to make sure that our parameters always point to the outwards, move our geometry outwards on both concave and convex corner, we just have to go ahead and invert the vector that we slide along. For the convex corner, we multiply by -1. So for the convex corner, it's going to be multiplied by 1. That means if we have to we invert it, and we're going to slide it outwards with positive values. So the -1 is just for the consistency's sake. And that's pretty much it. We have applied this logic for the offsetting of the corners. For the convex and concave corners. So that's it. I'm going to so now what I'm going to do is go ahead and add a couple more modules and see where we are now with our building, and then we're going to start working on some more new stuff. After a little bit of editing, this is what I have for my setup. So first of all, what I did is fix the bug that I made here. I didn't actually add my concave corner. I didn't name actually my concave corners on the set corners wrangle node. So this should be now fixed. I am updating these inside here. And also I created my concave corners. So you can see I have now concave corners for the building, and how they are made are actually very simple. Let me go ahead and go to the go ahead here. So basically what I have here is just I took the original corners, which is a convex corner. I went ahead and clipped it. I transformed it, I scaled it a bit, I mirrored it, and then just saved it out as a new geometry. And I did it for basically there are two variants for the first floor and two variants for the third floor, for the second one. And I basically just did the same thing for all of them, and I saved them out as a new geometry. So we have to go ahead and import the geometry inside Unreal so that we can create our instances for this geometry too. But basically this geometry is going to work just fine inside Unreal, since all the attributes are already set for it and the materials are all the same here, and we're just doing some basic operations like clipping and all of that, and the geometry should work just fine inside Unreal Engine. And the corners are being set in the modules. So I have so right now I'm just using one corner for each variant. So let me go ahead and say concave corners. So I am not using a corner for the third floor for the roof edge. That's because there's really no geometry that is suitable for those edges, and I'm going to show you how I actually went around for that issue. So I am creating my concave corners, and this time I am calling them F1 for the concave. That's going to be CC0, and F2 CC02. So you can see that concave is CV and concave is CC corners. So let's go to the building module. So inside our control, we are specifying our corners. So right now I am pointing the concave corners, but for third floor I am also pointing my convex module to the my concave module to the concave convex corner. So actually I want to have an ability for me to select let's say I want to no module to be copied there. I should probably go ahead and add an option for this menu to have a no module option. Let's go ahead and do that. Go to the parameter interface. Let's go to basically we should go ahead and add this option for all of our menus. So we have to do a little bit of editing. So what we can do is take this append function of the menu and then go to append and append 2 times, and I do not remember which one is the label, the value or the first or second value for these. So let's add no module. So okay, so the second append is actually the label of it. So the actual value of the parameter is going to be the first one, and I just want to leave it as a empty string. And for the label, say no module. You can maybe even add like that, no module. And I just have to go ahead and copy these 2 lines for all of these menus. Make sure you press apply, because from my experience, it won't save the menu. It won't update it. Basically, we want to discard these changes that we have made. So now we have no module menu option, and let's take a look at how it works in real life. So you can see, so in these corners, you can see that the roof edge is kinda created so that it has basically a natural overlap. So we don't have to even cap it inside here, as long as we have set our corners, our corner size for the third floor big enough so that it fills this gap. You can see, if you make it big enough, we have still some values to play with, but we have closed it up, and that's it. And for the concave module, let's go ahead and try to select no module, and you can see it basically discarded, since it didn't find this module. It discarded the concave modules at all the concave parts, and that actually looks really nice. And these concave corners really does add a little bit more of a polish for the whole look of the building. I really like them. So this is basically, we are done with the building as a walls. So we have to also add some doors, basically enter some doors to this building, but that can be easily done by overriding a couple of these modules that are on the first floor. So I'm going to actually now start my focus on the roof of this building, because the roof of the building is a big part of this whole process. So let's go ahead and try to work on our roof. And let's start our work on the roofs. So what I have here, I made a setup for the roofs, and I want to go through it because I found out this is the best way for me to showcase the roof logic, because there's a bunch of intricacies to it and you kind of have to see the end result, and I'm going to explain every step of the way how it is made. So the roof is going to come with a couple of options. So if you go to the control, under these roof controls, I have a ability to set the piece size. So the idea is that we only want to instantiate geometry, and we do not want to create new geometry. So taking a look at the asset pack that I'm using, there are basically only a couple of roof modules, and all of them are basically straight pieces. So if you take a look at meshes, general, and search for roof, so they're basically the kind of roof tiles two types of tiles, you will notice that they are already angled. So the tile is that, and there's another one, another type, this one, which I'm using actually right now here. So these are just the two types of roof tiles. So I want to make sure that I so which one is this? So this is the re-imported geometry. Basically what I want to do is make this geometry actually flat on the surface, because in our tool we have ability to change the angle for these pieces. So it's not going to be statically like a 30-degree angle, and since our building is going to be dynamically scaled, we need to also figure that one out, how to do scaling. But the idea is that we have to just go ahead and take this geometry and re-import it inside Unreal as on a flat surface, because we're going to do the rotation with our instance point normal attribute, normal and up attributes. And before I go to the creation of the roof, let me show how I am creating these custom geometry pieces. So to prepare for this tutorial, what I did is create a couple of custom geometry pieces, something like a combination of couple of modular pieces. It's going to be created into one generated piece that's going to be used as a gable. So I have tried to basically, these are four different modular pieces combined together into one this geometry piece. It's going to be combined, and the roof are being exported as a flat surface. And how I am doing it is pretty simple. So I'm going to show how I have combined my custom gable. So I'm using my file scrubber node, and I'm going through all the geometry that I have found. You can see there's going to be this wall floor re-arch gable. I'm just copying, then I am just matching it to the center, and I am mirroring it. And then I want to import these roof edges, and both roof edges, and then just combine them. And the important part is that we are using this as a whole geometry, since we want to create a new geometry from it. We create a new geometry, and one thing that I have to do is make sure that there are so the material assignment is going to be correct, as long as this material is there when we import the geometry. But one thing that we have to make sure that we do not have so sometimes a single geometry can have like multiple materials applied, and these materials come into Houdini as an index value. So basically there would be like a square bracket in front of this material path, indicating the index of the material for that static mesh. So we want to make sure that we remove those indices, because there are a chance that we are merging two pieces of geometry with something like two different materials, and then the indices would match even though the material path would not. And that, in my experience, would create incorrect geometry as material assignment. So basically what we are doing regular expression. We replace any square brackets with empty string, and that's basically it. In this case it's not really necessary, because there are no multiple materials for any one of these single pieces of geometry. But that's one thing that you can do to make sure that its materials are imported correctly. So up next, again I am rotating this geometry. I am assigning my tangent u and v, and you can see in this case it's a little weird looking. It's probably because of the mirror of the geometry. You can see that the effect looks fine on here, but on the middle it looks a little weird. So maybe I'm going to look into it a little bit later, but I'm not too concerned about it right now. So let's go back to the Houdini, and then I want to make sure my Unreal input mesh name. So this is we need to update our Unreal input mesh name to the path where we are going to import this geometry. So I have made basically a simple setup. Let me open this up. So this setup is, I have my two spare parameters. I have path and name, and we're just going to combine these path and name into the string that is required for basically we're going to create the same string that comes from the Unreal Engine into Houdini for any pieces that came from Unreal Engine, so that we not need to re-import this geometry to get this value, and basically saying where I'm going to import this geometry. You see, it's basically a path, and we have to give it a name. In this case, I call this static mesh roof gable 0. Then there need to be a dot, and there need to be repeating this name, because that's the format that all of these default values come from. There's a path, then there's a name, dot, and the name is repeated. And then I want to make sure I save it, and when I import it, I want to make sure that I import it into this directory that I have set up inside here. And the easiest way, if you're doing like a simple geometry, you can just go ahead and let me go ahead delete this geometry. Let's say I have saved this geometry into the Unreal Geo custom roofs. I'm going to drag this. So I have my roof gable 0. You can just go ahead and drag it into the file, into the content browser. You can see it's by default it's going to import as a roof gable. Then it's going to add also the extension. So this is going to happen if you're not using something like an import node from Houdini HDA. So you can just go ahead and manually rename this if you're doing like a simple geometry and something like not a lot of pieces. But obviously if you have a lot of custom pieces, you probably want to look at something like some variation of the import geometry node that I showcased earlier, where we are fetching the file name from disk and setting its name when we actually bake it. But for this case, I'm happy with this one. So yeah, and for the custom pieces for the roof, what I have here is my basic roof. But I also have two cap pieces, and the cap pieces are very interesting because they are basically the same geometry, only mirrored. And and the reason why I mirrored it, because I wanted to basically take my roof. So every one of these geometry pieces, I want to basically start with my start cap geometry. Let me delete this one. Let's do this like this. So I might have my. So this is end cap. Let's start with the start cap. So then I want to instantiate across the roof my long piece. Let me try to align this. Like that. And then I always want to cap with the end piece. And it's little, there we go. So you see, I basically want to across a roof instantiate as many middle pieces as I want, and I want to add with the cap piece because the cap piece has these chamfered edges at the both ends. But in reality, this is basically just a mirrored geometry, just the same geometry, only mirrored, because there wasn't like a cap pieces on start and end that this pack came with. So let's go ahead and implement this logic. So let's go back to Houdini and let's start working on this. So this is just a quick. So the custom geometry, I'm not going to talk too much about it. Basically, any custom geometry is being generated at its as a way that we need something like these corners, which I think I already talked about. So let's go back to the Houdini modular building. Let's go through this entire thing. So the reason we are setting up our building like this with the grids, this is because of this is going to indicate the roofs. So this is probably the easiest way for us to get the individual roof pieces, because if we would try to get something like individual roofs from here, it's going to be a little bit more difficult. So for now, I'm going to use this workflow where we input our grids together, merge them, and all of that. So let's start by setting our long and short edges. Oh, and I also forgot to showcase the parameter options that I have set up. So the parameter options are pretty basic, but pretty also important, because first of all we have ability to set the cap piece sizes for the cap pieces and for the main tile piece. So let me go ahead and change these values. So if I change the cap piece size, you can see we are now having these holes, because our cap piece is set that it's 0. More than 1. So we have to make sure that we align it just enough for it to cap out our geometry. So this could be made something like this could easily be made procedurally, but for now, for sake of speed of this tutorial, let me do it with the parameter. And then also there's the main tile size, and there could be like a and for the tile size, you can see if we change our tile size bigger, there's going to be more spaces between these. So we have to make sure that it is just enough so that it aligns. So usually these pieces are just enough for something like a round number. So in this case, my tiles are 4 meters long. So these are options for the tile sizes. So now we have ability to offset our long and short edges of the roof. So if you want to overhang and whatever the geometry we have ability to basically make this roof a little bit bigger, to maybe have overhang over the whatever we have here set up. And then we also can overhang the short offset for the gables. So if we have gables that has some geometry and we want to overhang it, it's going to overhang all of them. And you have to be careful because it's going to also overhang this one. So I will show some options for you to maybe to have some extra options for the how to control something that's something for the geometry for the short edges that intersect with other geometry. Then we have an option to change the steepness of the roof. So this is a very nice option to have because it's going to give us a lot of visual variety when we change our roofs. We can make it more steep or less, like that. And then we can offset our roof, which is just a uniform offset on the y-axis. So pretty basic options for the roof, but these are important to have. So for our roof to control it just a bit, so for it to have a perfect fit on the building. So let's start implementing it, and let me go through what we're doing. So first of all, I want to implement the short and long edge offsets that I showed. So this is actually pretty not as straightforward as I thought it would be, because there is because of the way that you would. I initially thought I just go ahead and calculate longest and shortest edges and then just extrude them, but sadly this creates lots of unnecessary groups, and we have to do a lot of group deletion and creation of new groups, and it gets pretty messy. So in this case I'm using the offset variation a little bit differently, how I'm setting up my offset. First of all, I am extruding so I'm running over each primitive. I'm starting by extruding our roof, and then I am moving it on the negative axis by the half of the extrusion. This will make sure that basically these extruded polygons are going to intersect at the middle of original plane that we are inputting. And then we are calculating primitive normals. And you might already see that the primitive normals for these edges are going to point outwards. And if you think about it, if you take our long edges and we add our vector values for both of these groups, we add this normal direction, we can start to offset the long edge. And also if we sample for these two edge groups the normals that they sit on, in this case we can move them outward with these normal options. So this is how we are offsetting them. So for this we are going to, so this is just for the normals. Then we are converting our input geometry, and we are calculating the maximum parameter with the maximum parameter labs node. Because the convert node, there's actually option for you to have a perimeter capture the length. So in this case it's called the parameter, so just left it like that. We calculate basically the maximum parameter for these polylines is going to be the length of the long edge of this geometry. And then we are using this to set up the group of the long edge. So we are using as per input reference to reference the geometry, and referencing this detail attribute max parameter we just set up inside here, and we are subtracting a very small amount from it. So this subtraction is just to make sure that we do not, so there may be, in this case I don't think it's even necessary, but there may be some precision issues, precision value that is lost between the nodes, and when that happens these values might not come in as they are, let's say, written inside this detail attribute. They might come into like rounded down or up. So I want to make sure that we always input a smaller number than we are, a smaller number at least a little bit. Make sure that accommodate some precision issues. In this case I don't think it's necessary because of there's only 4 decimal numbers after the dot. But we are basically using the edge group. We're setting a long edge, and we are saying that the minimum edge length is our maximum parameter. So that means that the smaller edges is not going to be selected. Small edges are not going to be selected. So let me color these, and then we can just go ahead and invert this group. And the inverted group is going to be our Gable group. And that's pretty much it for getting the short and long edge groups. But now that we have these groups, we want to go ahead and offset our edges. So these groups are going to stay the same, and our offset is going to happen actually on our converted line pieces, because right now they are 4 different primitives, and we can offset them in groups of 2 of the long edge and the short edge. So what we want to do is we want to transfer our normal that we got from this here, and this is going to give for each one of these primitives, polylines, a normal that points outwards. And then we just use a simple Vex code. Let me go through this. So we are setting our group type to primitives, and we are running over the primitives. And the one thing that I didn't set is this long, and I forgot to set is this long edge group. So the long edge group is going to set attribute value 1 on the edge that is the long one. So you should take a look at this in the geometry spreadsheet. You can see there's a long edge group. If you select these 2 primitives, you can see it is value of 1, because we are basically doing the same thing that we did inside this group node, where we are checking the maximum parameter, subtract a little amount from it, and we check if the current parameter we are running over is bigger than the longest edge, and if it is, that means that this is a long edge, and we set our value to 1. And if it's not, it's going to by default going to be 0, so we do not have to set value for the short edge. So then we transfer it, and for the offset we are referencing our control node long offset parameter, and we're making sure that our group is at primitive, group type is primitive, we are running over primitives, and for the group we say that we are running over the primitives that are at the long edge. And if you go ahead and check this out, so we're getting our parameter offset, we're getting our primitive points, and we run over each primitive point. So that would mean for this primitive there are 2 points for this primitive. So let's say we're running over these 2 primitive points, we are getting their position, and we are just adding to this position multiplied normal with our long offset parameter, and then we are setting this value. And as you might imagine, it is offsetting along that normal this point. So this is good because in this case, in the previous implementation with my with the poly extrude, the actually didn't work because the poly extrude doesn't like negative values. But in this case, it's actually going to work just fine because we are just offsetting. We can also offset on the negative values just fine. So this is in the end a more flexible implementation of the offsetting. And then we want to offset also the short one, and it's basically the same code except for the group is set up to the long edge equals 0. And now what we'll do is transfer these positions to our input geometry that has set up our groups. And it is actually very simple with single line of code. Since the point numbers has stayed consistent between our original geometry and the edge polyline geometry, we can just go ahead and use this single line v at p equals op input 1 underscore p. So this means that it's going to fetch the position attribute of the input 1, and it works really nicely. You can see we are offsetting our geometry, our original geometry. So this is a kind of and then we're doing it through for all of the edges, and we are getting something like this. So now what we'll do is go ahead and create a ridge. So the ridge can be pretty easily implemented. We basically want to take our shortest edge and we want to poly split it, and this happens inside here. So you can see after this for each loop we are splitting our geometry by the shortest edge. So this is how our ridge is going to be created, by the shortest by our Gable edge groups. Let me go ahead and go through this code. We are again running through every primitive, and for this poly split node we are referencing the attribute that we set up in this wrangle node. So the poly split node is very powerful because there are a bunch of ways that we can reference how we want to poly split geometry. And if we take a look at this split locations parameter, you can see that it's basically allows for different formatting on what we want to poly split. And I'm looking at, and I want to use this P, and then it requires for you to give it a point that you want to split between and the value at which you want to actually. This is going to cut at the midpoint. So some of these codes requires you say that at what location, basically at what percentage of the position between 2 points you want to split at. But this P, and then we just give it a point numbers, it's going to split at the midpoint. So this is exactly what we want. So I'm going to use this P and then just point to the point 1 and point 2 that we want to split. And you can see this is going to procedurally give us split locations if we create it inside the here. It's actually very simple. We're basically going to get our Gable group, and we are expanding this edge group. It is going to give us all the points that are inside the Gable group, and in this case it should basically be all of these points. But because this is the group, they will be ordered in the way that they are actually creating a poly. They are creating these polyline groups. So that means it's not going to come like the sorting of the points inside this array that we are getting for the Gable group is not going to be like 1 and 2 and 3 and 1. It's most likely going to be 0, 1, 2 and 3. It's going to go into the order in which they connect to each other. So this is why we can easily select our 2 points by the index of the array that we get. So this is where we are going to use, and the split edge is going to be P from the code. This requires a prefix P, and then we just take we convert our Gable group index 0, and then we convert our Gable group index 1 into string and combine it and create this attribute. And if you take a look at the detail attribute, you can see we have p, 0, and 1. Then we just poly split it and we get it to this all. And sadly, this poly split is going to delete our Gable group. So, but this Gable group is important for us to get our points. So we are using Gable group inside here, but this poly split node is going to invalidate this Gable group, sadly. You can see now it's basically gone because we have split the points between them. So that's going to be handled in this large chunk of the code where we actually going to instantiate our roof. Then we want to go ahead and create our ID per piece attribute, which is just a connectivity node, because right now we have at this point we have been running over each primitive, but this rich creation have created for each connected piece multiple primitives, so that now we need our ID attribute set up. So just create your ID attribute. I'm going to create it as a primitive for each connected piece, and then we have our height control option from our control node. This is where you're going to have ability to change the height of the roof. So let's go through this big code right now. So this is going to be most involved part of this roof. So first of all, we are running over each connected piece. We are converting lines our long edge group. So this is just to get the length of the roof that we are going to need our geometry to instantiate along. So we're going to convert to the edge, and we are computing the rest length. And then we are inputting into the new wrangle node as a second input, because this wrangle node is going to create our instance points that we want to, basically our instance points along the edge that we are going to instantiate our roof along. Now let's go through this code. So there's two parameters referenced that I showed from the control node, our cap size and tile size parameters. Let's go inside here. So we have cap sizes, and we also fetch our roof length from the second input of this node where we have our rest length. So these two are going to be the same, so we can just fetch from the primitive 0. It doesn't really matter. And now we want to calculate how many tiles. So the naming is the cap size is the caps, and the tiles are the middle big tiles that I want to instantiate. So we calculate how many tiles can we fit between the start and end caps. So we basically take a look at the roof length, we subtract our cap sizes. So we know our cap size, we multiply it by 2 and take our roof length and subtract from it, because we want to instantiate our geometry between the caps. And then we just go ahead and delete and then divide it by tile size. And then we just make sure that we get the smallest number from this. So we don't want to we want to make sure that we take the smallest value, and then we just use a floor function to make sure that we do not get a rounded up number. Then we are creating a variable that's going to be used as a position on the z-axis for new points. So the points that we are creating are always going to be across the z-axis, and we need to store a position where we want to instantiate next point on. So this is where the written length parameters variable is going to come in handy. So we're going to start our roof with the cap size. I'm going to add point, and we start at the very start of the world origin, so we just point to the 0, 0, 0. We set our point attribute, and for our new cap piece, I'm going to start it a cap start point. And then we want to add to our written length our cap size piece value. So this is going to make sure that next time we are referencing this variable into the position that we want to write to our next point, we're going to start at this point, because we have updated our written length variable. And now what we're doing, we are looping over the tile count, how many tiles can fit there, and we are basically adding this point. We are setting the x value for the new points. We are setting the attribute, and we are appending the value to the written length plus tile size. So for this each loop, it's going to increment, going to be bigger and bigger. And then we have written all the tiles that we can fit. We can go ahead and write the cap, our cap end piece. We cap end piece, and that's it for the point generation. And one last thing that we do in this wrangle is we are setting our scale. And the scale is calculated by the roof length, our input roof length, divided by the length that we have accommodated a size for. So basically divided by written length. So this should always be more than 1, because we're using this floor function. That means that we are using a floor function. That means there's always going to be basically a smaller, so there's going to be always a space that is smaller than one roof tile between the written length and the length of the roof that we are inputting in. So you can imagine that if our input roof is something like this long, and we are starting to instantiate our geometry like 4, 4, 4, and 4. So the another tile can't really fit to for this one. So if we would set another tile, this will be too big. So this is why we're using the floor function, to make sure that we do not go over the size of the initial roof. But that means we have to use a scale attribute to scale our shorter roof. So the geometry is going to be a little bit scaled to accommodate the exact size of our input roof. So this is why we are just dividing our roof length with the written length. This is going to create a attribute that is something like 1 point something, so it's always going to be more than 1 inside here, and we just set our detail attribute as a scale. So inside here we are setting the scale attribute as a we have set our detail attribute as a scale, and inside here we are just go ahead and set it as a for each point, because the scaling for each point has to be the same. And you will notice that only the z axis has to be scaled, because we are really working on the one axis for this instantiation points for now. So then we want to convert it to the polyline, and we want to go ahead and set up our normal attribute. So the normal attribute is very simple. We just put on a polyframe, and for my experience we have to go ahead and invert, so by default it's pretty weird, because you can see that whatever the polyline order whatever the point order is, the vectors point to the opposite direction than the next point is pointing to. So in my experience, we have to go ahead and invert this direction, and you can use it by using the attribute expression node, where you can select the attribute 10, and you can just use self multiplied by -1. So now the important part is transferring our roof angle. So this is where our up vector comes in handy. So the up vector is calculated from here. So this is another input from here. So what we're doing is here is so we are calculating a couple. So for now let's skip it. But we have basically want to get our normal of the roof. We are setting primitive attribute for the normals of this geometry. Oh, it's very small looking, but I guess by default this doesn't work. So basically you can see the normals on the primitives point outwards. If we want to transfer this normal to our polyline here, and this is very simply done. We are taking our vectors from the primitive 0. We are making sure that the x value is actually positive, so we always apply absolute function on it, and then we just set up our normal. So this is important because of the way that we are creating the geometry. Let me actually go to this extraction of transforms. So the transform extraction is important because right now we do not have any way for us to make sure that this roof is going to be aligned at the end with the input geometry. So you can see at the end of it we are getting all of these points and they are aligned along the roof. So right now we do not have any way for us to move it back to the basically to the roof ridge right now. So this is how we are actually doing the transformation. What we are doing is we are converting our ridge. We are converting our ridge group to the polyline. So this is going to be reference on the point, basically reference on the location where we want our points to be. Because at the end of it, we want our instantiation points to be along this ridge group. Then we go ahead and create a wrangle, and in this wrangle, we are taking second input as this ridge polyline. We are taking the point 1 and point 0 and 1 from those ridge, and we are looking for the vector of direction where this ridge is pointing to. And then we're using dihedral, which basically says this vector should look at the z-axis, because it should look at z-axis because we instantiate our geometry along the z-axis. So we take this ridge and we make it look to the z-axis on this direction. So in this case the input geometry is this one, but if we go ahead and take if we solo geometry something like this, where the input actually is pointing to the, depending on the point order, is basically pointing along the x-axis. That means we want to rotate it to along the z-axis, and this is exactly what dihedral function does. It takes the direction, and we say that if we want to look at the z-axis, and then it's going to calculate the matrix, and we just multiply our position with this matrix, and it's going to rotate geometry. And what we want to do is go ahead and we want to rotate our roof, and then we also want to store this rotation, this matrix, as a detail attribute inside this geometry. So we have now aligned it along the z-axis, and now I want to make sure that it is aligned along only the positive z-axis. And we can use just the basic match size node with the max min justification set, and in this match size node there's an option for you to stash the transform. So this is basically the same attribute, the same data that we stored from the wrangle, but we are storing another one which describes the transformation from this place to this one. And then we go ahead and calculate our normals, and then the normals are referenced inside here. And I'm using, and from my testing of this workflow, I found out that this normal should always that the x should always point to positive value for the roof to correctly instantiate. So I just made sure that it's always absolute value on the x, because the roof values will only have two values on the x. It's going to be either positive or negative. It's going to point basically along the x-axis positively or negatively, and I want to start by positive. So the values are basically the same, only negative and positive values. So I want to make sure that it's always positive, that I start with this one. And if you take a look at it, we are now, you can see we are now transferring our vectors pointing positive on the positive position. So now where the Unreal specific workflow comes in handy, where we want to transfer to our points our instance attribute. So this is where all of my roof geometry come in handy. So what I did is, let me go ahead and go to the modules. In the modules I created a separate merge node where I have imported the flat roof modules that I'm going to use inside Unreal Engine. So what I have here is imported these three pieces, and I have set up my IDs for them: cap start, cap end, and tile attribute that's going to be used as an ID attribute that are, so basically this attribute is also set on my instance points that I can correctly reference correct geometry for each one of those points, and I just have a merge node for them. So let's go back to the custom building, module building. So what I'm doing here, I am unpacking all of the geometry, and for each point I am checking the I am unpacking and I am transferring attribute ID. So this means that on the primitives I will have this ID attribute that I set on my in the module subnetwork. You can see I have my tile, cap, and start, and I have my cap, start, tile attributes on my points. So what I'm doing is for each one of these points I am finding the attribute value on my primitives, which I'm on whatever the point that I am running over. That means if I'm running over the point 0, that's going to be a cap start ID. I am finding this value on my instantiation geometry, and once I have found, I want to sample from the first primitive its Unreal input mesh name attribute. And once I have gotten it, I just want to set it as a s at Unreal instance point attribute on this point that I am running over. So this is going to give me an ability to have these Unreal instance attributes that references the roofs that I want to instantiate. So this is for the Unreal specific workflow if you're following along. So now I'm only covering I'm covering only one side of the roof. So the transform node is used to rotate it 180 degrees, and then I'm using the match size to so the rotation is going to make it face to the negative direction. So I want to make sure that I use a match size node to move it back to the positive, and I want to offset it by the cap size parameter from the control node. So this is because of the way that instantiation happens. We need to offset it, because let's say I do not offset it. Let me show how it would look if I do not offset it. So take a look at this copied point. You can see if I do not offset it, the copy geometry is going to have this unalignment at the end of it, because of we have rotated our points, and the instantiation happens in the way that instantiation happens. This is just the one thing that we have to do, that we have to also offset it by additional cap size, and this should make sure that the geometry is going to be correctly aligned. The opposite geometry is going to be correctly aligned, and then you just want to go ahead and merge this geometry together, and that's basically it. Now I want to go ahead and set a scale for our instantiation geometry points. We're going to set our scale for the actual instantiation geometry. So this is important because of the way that we are actually, so in our tool we have ability to change size of the roof. You see we can basically say tile offset, and since this is always going to be a single tile, it has to be scaled to accommodate entire roof. So this is a kind of a little bit of a challenge for us to implement. So how it happens is very simple actually. Well, we have to do a little bit of a thinking, but at the end I came up with some ideas. So first of all, we blast our big tile size to fetch the bounding box of this geometry. So we get our bounding box max from the tile box. So this is a big from the roof, and then we check how long is the roof. So inside here we are taking our roof and we are converting everything except for the long edge and the ridge. That means that we are going to only get our gable points, and both of these gable primitives should have basically the same rest length, and that's why we can basically take a rest length from the primitive 0. and scale is calculated by the roof side divided by the tile bounding box x value, because our geometry is going to be instantiated. Because how the tool works, we have our geometry along in this case along the x-axis. It's going to take the size of this one. It's going to roof side is going to be divided by the tile box to set the scale for this instantiation geometry. So this is the logic that powers the scaling across the roof to make sure that the roof size is actually accommodate entire custom roof size. This scaling attribute. You can see we are basically setting the scale for the x-axis only. So it can be pretty confusing because we have set our scale on the z-axis. This is when we are setting our roof, and now we're setting our scale on the. So we set our z-axis inside. We set our scale inside here for our initial scale, which was from here. You can see it can be it can get confusing because we have already set scale for the z-axis, and now we're doing basically the same, only we are setting the scale only for the x-axis for the roof tiles. So it's kind of have to know exactly what kind of values we are setting, so it can be confusing. And since we have now only set up our values only for the scale value that's going to be read by the copy to points node, we actually want to also accommodate the physical space for these instantiation points. So this is why we're taking a transform node, and we are referencing the point attribute scale z value. You can see we are basically moving our points across a bit. So this means that if I disable it and take a look at our copy to points, you can see now the tiles overlap each other because the points has not been also appropriately scaled. So if I enable it, you can see now the tiles do not overlap each other. So this is also important thing to add. So, and now how we actually getting these points back to the reach position. So this is where the attribute transform node comes in handy. So first of all, since we stored our transformations from both of these operations on the detail attribute, we want to transform this operation to our points. So use the attribute transform, and just from the detail transform your x from 0 and 1. And then you can use transform by attribute values, nodes. And you can see at first I'm doing it in the opposite order that I did for the initial geometry that I transformed. I am moving it first of all to the geometry that is aligned along the x-axis. I'm using x form 1, and I make sure that I press the invert transformation. And then I'm using the same thing for the x form 0, and making sure that I also invert transformation. And that's basically it. We have now moved our points to match exactly our roof. And then we want to set up our ID attribute for this group of points, and this time it's just a simple block begins fetch metadata node, and we're just setting our piece attribute, which I'm going to use a little bit later. So I think I'm going to use it, so I'm not really sure, but this is a good idea to separate each roof instance points right now. And so yeah, so this geometry is ready for the Unreal Engine instantiation. So this is what I showed inside here. I just saved these points, and if this geometry is in the content browser, it's going to be instantiated across here. Or if you're using this inside Unreal, only inside Houdini, you just get your piece modules that you want to instantiate, use copy to points, and use your piece attribute as an ID. And you can do some matching of the size, getting the original geometry from instantiation geometry that we did before, and you can basically place this roof however you want. So this is going to cover the creation of the roof. So now we have a couple more challenges. So first of all, we want to create our gables. So gables are going to be interesting thing to do, and also we probably want to do add some doors to the geometry. Before we go ahead and create our gables, I want to loop back to the topic of importing custom geometry inside the Unreal Engine and how can we handle it a little bit easier when we are creating it. Because I wasn't really happy how I explained it beforehand by dragging geometry inside the content browser. I want to talk about how can we set up our attributes so that they automatically are being placed in the correct folders when you bake out the digital asset inside Unreal Engine. So let me show my setup, and I'm going to import my geometry from the start. So let's start by setting up of the geometry and attributes. So ideally you would not have to do this process inside the same heap file where we are creating our module building, because at this point all of your modules should be already set up and they should be on disk. But in this tutorial I am actually making these custom modules inside the same heap file, and I'm not really all that happy about that, but for the tutorial sake it's going to work. That's fine. So I'm just basically taking the same geometry, mirroring it, taking some of these edges, just combining them into something that can be a gable for my roof. So the same material, I resolve material conflicts, the same one I showed. Then I'm also rotating this tangent U, and in this case it's even not necessary because the tangent attribute that came from the Unreal Engine in this case is actually 0. So this wrangle doesn't really do anything. So I think I'm going to leave it at that. So it doesn't really matter, and I don't even have my how my X-form setup for this one because of the geometry. Because I am not even storing the rotation information at all because geometry comes into Unreal Engine just fine. So that's fine. And the issue for me was for the weird effect is that I actually fused the points when I mirrored the geometry. So this is where you saw that weird kind of flat geometry across the middle. I unchecked this consolidate seam and it fixed the issue. So that's one thing to note. So, but for the sake of the tutorial, I'm just going to leave it at that. And then we have to figure out how we want to align this geometry. So in this case, I went ahead and centered my geometry across the z-axis. So this is done because we want to actually scale our gable to align with the roof. So it has to do some scaling, and the best way to do our scaling is on both sides uniformly when our geometry is at the center and on the positive. Entire geometry is on the positive y-axis. So this is why I went ahead and used the match size and use the justify y and justify z center. And this is the important part on how the geometry is going to come into the Unreal Engine. So let me go ahead and explain this. So we are setting up these two attributes that control the name that when we bake out geometry inside Unreal Engine, and where the geometry is going to be saved in which directory. So you can see I have my two parameters, my path and name parameter. So this is the custom path inside Unreal Engine content browser where I want to save the geometry, and the name I'm going to use on it. And the name is actually expression that uses the opName function. So that means I can see easily the name of the object that's going to be saved. If I go ahead and change the wrangle node, you can see it has updated this one. So this is a lot better way to set your name, because you can actually visually see in the network what the name is going to be exported with. And then we have to go ahead and combine our path and name attributes into the into Unreal input mesh name attribute, where I explained that it has to be a path and then forward slash and then 2 times the name of the geometry added, separated by the dot, and the bake folder is going to be our bake folder here, and that's basically this attribute is going to control where the geometry is going to be baked out when we bake it inside the Unreal Engine. And that's pretty much it for these, and I just go ahead and save this geometry. And then this geometry is going to be re-imported inside this very heap file when we are setting up our modules. So let's say I have my module roof module, or let's say my gable module. I go ahead and import I import back this module that I have just saved. Let's say we have saved all of these, and the save folder for me is doesn't have to be anything like this path. I just saved it in my directory. In my directory, I have two different. Basically, I have my Unreal geometry, I have my custom folder, and this is where all the custom geometry is gonna go in. So my roofs, my 4 different roofs, and corners, 4 different corners, 2 different directories, and we now want to go ahead and import everything inside here, inside Unreal Engine. So let me go ahead and go to Unreal Engine. So I have already imported them, but what I want to do is go ahead and delete it and show you from the beginning how to import them. You can see our gable came in really nicely. So I'm going to go ahead and delete both of these directories. Just go delete them. I'm going to use my import geometry node. Let's go here. So let me go ahead and copy this custom directory inside. So I'm going to put it to the pdg cook type, put it in directory. So I can select the subdirectory, but since I want to get both of these directories that I want to fetch from, I'm just going to put it on recursive and leave it at everything. And then I can go ahead and cook output. You can see geometry is already filling the level, and now we have cooked out all of our egg objects. And if we have set up our attribute of the bake attribute, you can just go ahead and say under the pdg asset link. So this custom folder should now populate. Just press bake. You can see we have our 2 folders, and our corners and our roofs are automatically placed in that attribute value that we set up inside the Houdini. And since our attribute is correctly set up already on the saved geometry, we do not have to re-export this same geometry because the path is already correct. Because the path is already set up correctly when we save the geometry from Houdini. And this is basically the way that I did it for this custom geometry. So there's definitely, and then you can just, not to mess with this, just create a new level, and the geometry is going to be saved. So this is the way that I made this. I imported the custom geometry. So this is not probably the most optimal way to do it, but for this tutorial it's going to be, since we are covering already that so much, it's probably going to be just fine. Let's go back to so I'm not going to talk much about this importing and exporting between Houdini and Unreal Engine anymore. And now let's talk about how can we implement our gables. So the gables are going to be pretty straightforward. So we have our gable geometry. I just showed off, and I want to go ahead and get the points that I want to instantiate on. So I'm going to start by this input quad that we are building from our geometry with the setup long and with the setup of the long edges and gable edge groups. So this is where all this happens inside this loop. So we are looping through every primitive, and we are outputting only the instance points that we're going to instantiate our gable geometry across. And the extra option that I have added to this gable loop is to check for intersections. So in this case, let's say my roof is very close to the middle, and since my gable is kind of like has this extruding geometry, I want to make sure that I do not create gables for the roofs that are actually intersecting with other geometry, like in this case. So I have my option inside the control node to check for intersections. You see, if I uncheck it, I am now creating these gables also inside here. So this is one option that we have to also handle inside this, inside the for each loop for the gables. And you can imagine that. So you can imagine that if we have our geometry like here, so this is maybe okay for us to have a gables between these because of this. Otherwise, it would leave a hole. Obviously, depending on your gable geometry, whatever is more appropriate for your use case. But in my case, I'm just going to move it back to a little bit like a middle. So let's go through this gable setup. So we're looping through every primitive. We are again converting to the lines. We dissolve everything except for the gables. And now we want to set up our check for intersection switch. So this is just reference to this control toggle parameter check for intersections. So if we are checking for intersections, this is probably the most involved part of this loop. We are using these two extra inputs for this loop. So first input is our entire geometry that we want to check against. For intersections. And also we have our meta import node that's going to be counter node, where we want to reference our iteration attribute. And that's going to so this is because we do not want to include in our intersection analysis our geometry that we are now looping over, because if we go ahead and start checking for intersections for these 2 points against the entire geometry, since inside the entire geometry is obviously our geometry that we are looping over, our piece that we are looping over, it's always going to find the intersections. So we need to have a way for us to remove the current piece that we are iterating over to remove it from the intersection analysis. So we could do it by a blast node. You could basically put out a blast node and delete the primitive that we are looping over right now, and then connect it inside here, and it would be a little bit easier. So, but in my method, I am using the intersection function, and the intersect function has the ability to check for the group. So basically we can specify which primitive to match against for intersection. And since the iteration number for each loop is actually equivalent to the primitive number in the whole geometry. So that means if our iteration number right now is, put it in single pass 1, so when this geometry comes in, the primitive number is going to be 0, but I do know that since the loop is going in the order of the primitives, in the primitive order of the whole geometry, I know that my iteration attribute value is equivalent to the primitive number of the whole geometry. So that means I can use this attribute to exclude this geometry from the intersect analysis function. If we take a look at this code, we are getting our 2 vector attributes that's going to hold the data that's come from the intersect function. We are checking for the current iteration attribute, so this is going to be input 2, which is this metadata, and then we want to create our string group that's going to be used inside this intersect function. So you can see that's basically asterisk and then the caret except our iteration value. So this is just like a string you would use in a group node to exclude some primitives from your group's like that. And then we're using this group inside the intersect function. So for the intersection, we use our current position, and the direction we're using, basically we're just pointing upwards to check for the intersection. And then hit position and hit UVW is going to be written out. And the integer value that this function returns is going to be the primitive that has been hit. And if this and if we have hit something, we want to make sure that we remove that point. So we just put down if the hit primitive is not equal, so if it hasn't hit anything, that means it's a -1. So that means it has not found any primitive. But if it has, we want to go ahead and remove that point. And this is done by e at pt, basically current point number, and 1 is to remove also the primitive, I think. You can see it has the ability to also remove that primitive, and we definitely want to use that because it's not even valid for us to have a 1 point that we basically, if the 1 point is off the edge, that means that gable is not valid already, so we just want to go ahead and remove it anyway. And that's basically it for the intersection checking of the intersection. And this is just a toggle. Up next, we want to have ability to also offset our gables. So in the final method, I have a ability to offset the gable, because whatever geometry we have, we probably want to align it a little bit to make sure that it aligns with the roof. So the offset is also pretty important. So the offset goes into the offset is basically the same thing that I did in the previous loop, where I extrude geometry. I move it by half of the extrusion downwards and calculate normals. Now I have a normals that points outwards for each one of these roofs. Then I transfer the normal for these gables, and then I again use the offset code that I showed off before to have ability to offset the gables. And then I want to go ahead and adjust the vector, because if I do not adjust vector, right now the way that I have rotated my gables in the geometry, you can see that something like here, you can see the gables are actually pointing basically because of the geometry is going to be aligned along the normal vector. You can see it's, since our vector points outwards, its geometry is aligned along the network, along the normal vector. So I have to go ahead and the offset is a bit too much. I have to go ahead and rotate it -90 degrees. So you can do this with the vex code, or you can use the attribute adjust vector node. You basically adjust direction only, operation rotate, constant rotate, -90 degrees. And that's basically it. And one last thing that we want to set up for our gables is ability to dynamically scale them. Because in the end result that we got here, you can see that if you go ahead and move some of these walls around, you can see that our gable should also dynamically change scaling for them. So let's go ahead and implement this dynamic scaling right now. So how it's done is actually pretty simple. We just need to do a couple of references of where to get our data. So first of all, in this wrangle, we are inputting our points, since we want to set up our attribute on our points. So we have our dissolve node. So this dissolve node is used for us getting the rest length of the, basically how wide is our shortest, basically what's the size of our gable, what's the width of our gable, to get the that value. And then we also want to get the size of our current gable that we want to instantiate, because it can be in different sizes. We have to make sure that we get basically the bounding box size. In this case, I'm basically just going to put down object merge, and I'm getting all my gables from my modules subnetwork. And inside this code, let's go through this. So I get my steepness. Also the steepness, remember the steepness attribute is just from the, basically the steepness attribute is the same as how high our roof is. So this also can be used to, is going to be used to calculate the scaling on the y-axis for this, for the gables. So we get our steepness, we get our gable module, and gable module is from my control node that I also set up the same way that I set up my convex and concave modules with a menu, which is basically says that okay, give me all my gable module, which I'm going to. So in this one, I'm going to show off the way that I set up a little bit later. Also this one, but it's basically the same way. We're just going to check the value of this parameter gable, but what gable module we are using. Because right now I just only have one module, but there can be multiple modules that we can instantiate randomly with our choosing. So let's go back to this. So get which module we have selected to instantiate. And then we get the width, which is from the gable group. What's the rest length from our input 1. And then we also have ability to manually adjust scaling also. And this is just a vector 2 parameter. Because we want will only have ability to scale on the, basically on the z and y axis. You can see if I start to play around with this one, I can adjust scaling, and this is necessary because of the different geometry that we can input. It's probably a good idea to have one last manual adjustment for the gables. And the idea is that we get our bounding box for our gables. So this is interesting. We are getting our gate bounding box size from the second input where we input all our gable modules, but we are using the group to sort which gable to get our bounding box from. Because if we, in this case I don't have set up, but let's say I have multiple gables that are in different sizes, the overall bounding boxes of the entire geometry is not valid data for me to see how it should be scaled. So I just want to use the bounding box of the selected geometry that I am instantiating from this parameter. So I'm using that parameter value to check the bounding box on that geometry piece, and I'm just checking. And the scale and width is very simple. We just go ahead and width and steepness is being divided by the gable bounding box z and y, and then we're just setting our scale attribute 1 scale y plus the manual scales x and scale z plus the manual scales y, and that's pretty much it for the setting of scales attribute for the gables, and it works actually really nice. Before we go ahead and start overriding some of these modules for the doors, I wanted to talk a little bit about improving this network. So what I did is basically I created a couple of subnetworks, and you can see I basically have all the big things that we have done this far. I have basically set them into the subnetwork. So something like a corner creation, I have put it in its own subnetwork, and something like this for because of if looking at the overall network, when everything is laid out in one level, it's kind of like confusing, and you'll be thinking like, where should I start? So definitely something worth doing, putting some of the big things, kind of group them together inside its own subnetwork. But just to remember that if you put something in the subnetwork and the parameter references, if they reference our control node, that's going to be fine. Houdini is going to automatically add basically 2 dots to dive upwards one more level, but for the hard-coded references to our level, to our control node, in something like like something in a roof where we set up our tile name, where we're getting our tile name, you're going to have to manually add 2 dots, and basically have to add 2 dots more to find the control node. It's not going to do it automatically. So that's one thing to note about putting your logic inside the subnetwork. The vex code is going to have to be altered a bit to find any references that you have here. Another thing that I wanted to talk about, how I have updated the finding of modules which to instantiate across the geometry. So if you remember, in the roof geometry, what we did was we're creating an ID attribute, and there were basically three values available for the ID attribute, which basically it was a roof start end, cap start, cap end, and the tile. So I went ahead and changed it a bit. So what actually I'm doing now, I am actually getting the module names, basically cap start module, cap end module, and tile module from my control node. So I have added options to fetch these names from there. So this is going to actually allow us to dynamically select which geometry we want to instantiate across our roof by selecting from the menu. So if you go to the menu, you can see we have basically under the roof I have cap start, cap end, and tile parameters, and they are basically set up just as I showed previously. Let's go to the cap menus. You can see we are basically doing the same thing. We're getting our primitive attributes, module name, and then if it starts with cap end, and as long as your naming is consistent for each module type, it's going to, under this menu, it's going to finding all of those modules. It's going to set the module name underneath here. So we are basically done with the attribute ID because it doesn't really make sense for us to have two different attributes for the building from pattern node, which uses a module name attribute, and the custom logic for our roof was the ID attribute. So it doesn't really make sense for us to use two different attributes. So I went ahead and basically in my modules I introduced module name for all of my custom geometry. So you can see that inside, or something like for this gable, I am basically go ahead and setting the primitive attribute, module name, gable 0, and that's it. And that means that we can have different gable types, and we will be able to select them from menu and update them in real time. So we won't have to go ahead and change the geometry inside here. We can just select it from the menu, as long as we have merged them together inside this out gables merge node, and that's basically it. And now let's finish our building with some doors. So what I have here, I taken my geometry compositor node and I just went ahead and composed a bunch of geometries together, and I have basically just a first floor door like this. And I'm going to treat it just like any module. I'm just going to put down labs building generator utility, and I'm calling this F1 door V0. And then just merge it together with all the other modules that have this utility generator. So we could use these doors inside any pattern as we want, but in this case I actually went ahead and manually overwrite as one of the points in the first floor. So this is actually really easily done. So when we get our points, we're going to put down a split node, and we're going to use only the points that are smaller than 0.1. That means basically get only points that are in the bottom, basically that points that store information about the first floor. Then I'm going to use a group by range node. This depends on how many doors you want, and let's say I want for my building just a one enterable door. You can use just basically a range filter. Select one out of n points 0. That means that it's going to select only 1 point between all of these points. And what's cool about this, you can go ahead and let's color these points. So you can see this red point. You can basically go around and choose where your doors are going to be. Let's say I want my door somewhere like in this corner, maybe like here. So this point is going to be so this module is going to be overwritten with our doors. So in the wrangle, it's super simple. We're going to take our door module. So the door module is going to be again in our control. I just went ahead and created this door tab, And I am again using my my Python script to have only F1 doors modules, any module that start with F1 door. Select that one, so we can, if we have more modules, you could select which doors you want, like that. And then we just overwrite that point. So we are only iterating through the doors group that we set up inside here. We just overwrite this value. And it's going to set the module name to that door. And then we just merge together from the split node second input all the points together, and basically everything else is the same. And the result is, as you might imagine, we have overwritten our module. And if you go to the group node and start offsetting, you can see we can basically put our doors wherever we want. And now let's talk about a couple of pitfalls to look out for when combining this geometry together. So I want to quickly go through the setup for the geometry, for the point cloud for the Unreal Engine, and for the Houdini. So for Houdini, it's super simple. It's basically nothing new that we have to do. So we have gotten our points with our temporary corners. We then basically got our corners. We assigned module names for our corners. We got our wall points by deleting the temporary corners. We overwritten our floor, our door module, merge them together. And this is the one specific for the Unreal Engine, so let's ignore that. So for Houdini, these points can be used basically again. And I'm making sure that I do not instantiate this geometry, because basically this geometry, with my setup is already all of these, doesn't store really actual information on disk. It's basically just a references on the disk. It doesn't store in memory any of the information. It's basically just references on disks, and it's going to be a lot easier for us to work with these packed primitives individually. Because if we would go ahead and pack it again, you see that every module has been basically packed again, so we will have to unpack each one of these primitives again. So just make sure that you do not pack an instant geometry. So we have now combined them together, and what you can do is just go ahead and copy the points again using the piece attribute module name. And what you can do is basically just point it to the all of the geometry that we have imported. Basically this is the same object merge node as here. It's just references this node. Object merge, so basically all of the module that we use for the building is again piped into the copy to points, and we have recreated our geometry with our corners instantiated and all of our modules updated. And for the on the Houdini side, for the roof, it's basically we got our roof points, and then we just go ahead and basically do the same thing. We have our roof points. For demonstration, I think we can just point it even. So we just got our roof points. We have moved them around a bit to match the location, and just copy the points again, the same thing as with module name. So you could probably even basically merge these two together to copy, but the difference is that we need also make sure that our roof is on top of our building. So this is why I'm using this is why I have set up previously. I basically took the geometry merge, and we are basically offsetting our roof, our points before copy to points, and we're making sure that it always sits on top of the bounding box of our main geometry, like that. And you might notice these two for each loops. This is basically Unreal instance point setup. So for the Unreal, we have to do things a little bit differently, because we want to reference geometry that is already on disk. So let's go through this. So once we have instantiated our walls, we want to go ahead and loop through each one of these packed packed points. So you see that basically every one of these pieces has been we can select it individually as a piece, and we can go ahead and loop through it. So we just loop through it. We extract the point from it. So this is basically we're running through the primitives. So we want to extract that point from that primitive, It is going to be our instantiation point to take on the send to Unreal Engine. But before that, we want to unpack this geometry and fetch the Unreal input mesh name attribute. And we want to set this value as a Unreal instance attribute on our point that we're going to instantiate. And we are just doing true for all of the points. So at the end we should have something like, so let me show at the end we should have basically points with only a couple of attributes that are necessary for the Unreal instance to work. And now this covers the instance points for the walls. So for the roof it's a little bit different because we basically created our points manually. We have already set up our normals up and scales from the previous network, and but we do not have to unpack because right now these details needs to be unpacked to check for the Unreal instance attribute. But in this point we do not have to unpack it. So what we do we are looping through this time we are through the points, and we are inputting our all geometry we input. We basically and then we go ahead and blast all the modules except for the one that we are checking for the module name, that point that we are now looping over, and then we are unpacking that packed primitive, and then we just go ahead and get the Unreal input mesh name again and set it as at Unreal instance attribute. And we just do it too for all of them, and that's basically it. Then we match size to the building that has been already created by copy the points, match it to size, then combine all the points. Then we can go ahead and delete all the points, all the information except for the normal, up, Unreal instance and scale attribute, because basically nothing else is really needed. And for the geometry to inside the Unreal to come into the center, you can put down match size node and just center it at the world origin. And then you can just save it and let's check it out how it looks inside Unreal. And if everything looks correct, it should come into Unreal Engine just fine with correct scaling applied. Well, almost. I will talk about a couple of things that is actually incorrect in this building because of the scaling issue that we have. So you will notice that these stairs and these railings do not look correct. So this is because of the scaling issue that I found that happens inside when transitioning data from Unreal from the Houdini to the Unreal. So let me go through this and explain a bit. So you see that our instance geometry inside Houdini looks actually correct. It has been correctly scaled. So this is because this issue comes from the fact that because of the axes are being inverted between the Houdini and Unreal, between Houdini and Unreal Engine. So let me show the thing that first of all, so for my geometry compositor node, I want to show how something like this would come into Unreal without using the building from modules node. So I have it basically, I just copied the same modules I copied inside geometry compositor, and all of these basically attributes are ready for Unreal Engine and for instantiating, or even inside Houdini also, because it really needs only the normal up vectors to instantiate correctly and scale. So, but we have already set up scale. We went ahead and scaled our interior box a bit. Now I want to prepare the geometry for the Unreal instances inside Unreal, and this is basically the same thing. We go ahead, loop through each primitive, extract point, and then we unpack that primitive and get our Unreal input mesh name, and that's it. And then we save it. And let's take a look at how in Unreal this geometry would come in if you're not using or building from modules node. So I have this set as a test module. So you can see the geometry actually comes in correct. It is correctly scaled and everything looks good. If I go ahead and basically I just go I can just go ahead and start scaling some of these modules. Maybe like this one. You can see now I have scaled it. Let's save it. Now let's go ahead to the Unreal and recook it. So you can see we have correctly scaled on the correct axis. And I have tested out, axes are all correct. And now let's take a look at the same module being instantiated using the building from modules tool. So you can see that this is incorrect. So you can see that the scaling, so we know that these modules that we instantiate are going to be most likely scaled at least a little bit because our tool can dynamically adjust wall sizes, and it's not really for us. We can't really precisely guess how big of a cube we should make to make exactly match modules to its size. So it's going to do some scaling. You can see that the scaling has been applied correctly to the geometry that has been aligned along the y-axis on the Unreal Engine. So take a look at, let's go through this instance geometry and let's find our doors. So you can see the doors has been applied on the y-axis, it's scaling. You can see it works correctly. So this is because our geometry has been aligned along the y-axis in Unreal Engine. And let's go to some of these geometry that has not been aligned correctly. Let's go ahead. We should find our stairs. So okay, so the stairs. Take a look at the stairs. You can see it has applied the scaling also on the y-axis, but because of our geometry is actually not correctly aligned, it's going to start basically aligned also y, but our geometry should be rotated, because this geometry basically going to be always should be along the y-axis. So we should align it correctly, just like we have aligned our doors, like I showed, to align it along the along the wall, along the y-axis. And also for these pillars, you can see it's actually scaling says 1. That's because this is a hierarchical instance mesh component. That means that it basically instantiates 2 geometry pieces. So we have to go down to the instances, and how many instances we have. You can see it basically has applied the same scaling, and you can see it's basically in that direction. And we go ahead and open some of this geometry. So you can see even though the longest basically it is aligned along the y-axis, but obviously we want it facing. You can imagine if this is the wall. We want to make sure that this face is actually it is aligned along the x-axis for the scaling to happen correctly. So this is one thing to note about these instances that we have to make sure, at least in the current implementation of the tool. And I'm going to talk about how we are actually applying this scale. And there's probably there could be pretty easy workarounds if we somehow tag the geometry to basically apply scaling to the the scaling then should happen probably on the x-axis. Let's find the stairs. So for geometry that is not correct, so it probably should happen on the x-axis. But the most easiest way for you to do it for now, if you want to instantiate geometry using the building tool, is just align it along the axis that's going to provide this correct scaling. So let me show how I have done that. So these modules are going to try to fix them, but for now I'm going to show how I'm actually doing the actual scaling. So let's go to the scaling has been, so this is interesting because we are using our modules, and my geometry compositor node has already set up some scaling. So you remember that something like this interior box has been already scaled. So you have to accommodate this scaling for the instances inside Unreal Engine also, because since this geometry is just a reference to geometry, so since we're going to only transfer the points, so that means our scale attribute has to accommodate the scaling that we have done on these modules, and also the scaling that the geometry building from pattern node has applied. So this is where the scale attribute is going to be automatically created by building from pattern. If you take a look at the scale, see the scaling has been applied to some of these modules. So what we do is we store the scale into separate attribute. So what I did is basically just say underscore scale equals v at scale. We store this attribute because we're going to now again copy to points this geometry, and now we're going to use the scaling from all of our modules. We're going to multiply this scaling, this stored scaling, with the scale that these modules hold, which we do inside here. You see that v at scale, we just multiplied by v at scale that we have stored. And I have made sure that all of my modules have at least some sort of scaling. Basically, all of my modules should have a scale attribute. So this is fine for so I'm not really doing anything special for the geometry compositor node, because the scale has been already applied. But in instances where I'm not using the geometry compositor node for something like so where some of them I'm just importing them as a packed disk primitives. For something like for this Gable, I am just manually setting the scale to 1, because if some of these modules do not have a scale attribute, it's going to default to the 0. That means we're going to multiply 0 by the scaling attribute that has been applied to the module, and that means basically our geometry would not be visible inside Unreal Engine. So this is not what you want. So I have made sure that all of my modules that I'm using to instantiate, we actually have some sort of default scale attribute, which should be 1. So yeah, so this is a couple of things that you have to watch out for when you want to instantiate geometry along these walls. The correct rotation to the modules. So this is one thing that I was pretty confused about, but the more I looked into it, it actually started to make sense. I hope it wasn't too confusing for me to change a couple things around, but since I think I found the better way to do things, it would be for me to best explain the method for me changing things up and explaining why I'm doing it, because it would make at the end a better tool to work with. And to end up this tutorial, I wanted to show how we can start to think about the improvement of the tool. So first of all, we have a lot of information already available for us to work with. So first of all, we can start to do something with these roofs. Since I had a goal to only using the instantiated geometry, I am a little bit limited with the geometry that I can create. But if I have something like this roof, I can think about maybe start creating my roof from the geometry from this entire quad. And if I do not want to use the modules from the asset pack, I can start to create different kind of roofs. That could be interesting. I have this roof geometry. I can start to maybe instantiate some towers across the roofs. That should be pretty interesting too. I can add some geometry across the ridge. That's also very common. And then if you want to start working on the interior, so the interior would be a little bit more expensive because these modules were not created for the interior. We have no walls, so that would make us to have to basically create some walls, also interior walls, but that should be pretty easy also. So we could start to think about creating the interior for the building, and this also comes with the floors. We can start to think about maybe boolean out, get some stairs. So there's really a lot of possibilities that I also want to cover in the future. And one thing that I wanted to say, if sometimes the geometry is not being loaded into the viewport, what you can do is try to go to the labs and reset viewport. It can be pretty buggy sometimes. You're not going to by not showing the viewport some instantiated geometry. So I think that's going to be it for this tutorial. I hope you found it useful, and see you next time.